Right now, as you sit still, the ground beneath you is rotating at over 1,600 kilometers per hour. And yet this is nothing. Out there, rotation reaches speeds that tear worlds apart. The universe spins on every scale, from tiny worlds to colossal galaxies. This massive movement happens continuously, but you don't feel it. There is no violent force throwing you off the surface, no rushing sensation in your chest. The rotation of Earth is so constant and uniform that it slips beneath our perception. But this steady turn is not unique. It is one example of a universal pattern, one shared by every planet, every moon, and every star. Jupiter completes a full rotation in less than 10 hours. At its equator, the planet's surface races through space at more than 45,000 kilometers per hour. Saturn rotates only slightly slower, and its flattened poles reveal just how much speed is locked inside its bulk. Even Neptune, far out in the cold reaches of the solar system, spins with remarkable speed. Across these worlds, rotation is not an exception, it is the rule. This motion did not appear by chance. When a cloud of gas and dust collapses to form a planet, it conserves its original angular momentum. As the material pulls inward under gravity, its spin accelerates. The same principle applies whether the object is the size of a small moon or a gas giant many times the mass of Earth. What begins as a faint twist during formation becomes a rapid and enduring rotation. But what we see here is only the gentle beginning. In the minutes ahead, we'll push this rotation to its breaking points, from planets that nearly tear at their equators to neutron stars spinning hundreds of times each second, and finally to black holes twisting space-time itself. Then we'll pull back even farther to watch entire galaxies turn on invisible engines. This is the story of how rotation, the simplest motion in the universe, becomes its most extreme. But this speed has consequences. The faster a world turns, the more its shape distorts. Gravity pulls inward while centrifugal force pushes outward. At the poles, the surface is drawn closer to the center. At the equator, the surface is forced outward, forming a bulge that can stretch thousands of kilometers. Every rotating world has a limit. If the spin grows too fast, centrifugal force can overcome gravity and tear the planet apart. That threshold is called the breakup velocity, the critical point beyond which no world can hold itself together. Some planets have already approached this boundary. Their shapes, speeds, and structures reveal just how close nature can come to breaking its own balance. But planets are just the beginning. If we climb one step up the cosmic ladder, we reach stars' colossal fusion engines where rotation doesn't just shape weather or magnetic fields, it helps decide how the star will live and die. Here, spin is no longer only about balance. It becomes a force that can sculpt a star's entire fate. The shape of a spinning world is never perfectly round. A planet that rotates slowly like Earth bulges slightly at the equator. Its polar radius is about 21 kilometers shorter than its equatorial radius, a difference almost invisible from space, but proof that rotation leaves its mark. A planet that rotates much faster like Jupiter shows that effect clearly. The equatorial bulge of Jupiter measures more than 9,000 kilometers. Its poles are noticeably flattened, a visible scar of the forces locked inside its spinning mass. In short, faster rotation always pushes against gravity, and every world has its breaking point. For gas giants, this limit is not theoretical. Saturn, with its rapid rotation and relatively low density, is extremely close to this critical point. Its shape is so oblate that its diameter at the equator exceeds its polar diameter by more than 10%. If it spun just a little faster, its outer atmosphere could begin to drift away. Solid planets have higher tolerance because their internal structure resists deformation, but even they face an ultimate limit. Beyond that, rocks crack, layers separate, and the world itself can break apart. Astronomers have also observed exoplanets spinning near their structural limits. Some of these hot Jupiters rotate in sync with their orbits, while others spin rapidly under intense tidal forces. Their equators stretch so far outward that their silhouettes appear slightly flattened when passing in front of their stars. The subtle distortions give scientists a way to measure their spin, revealing that rotation is not just common, it can be pushed to the edge of stability. A spinning planet is a system in tension. Gravity fights to hold it together. Centrifugal force pushes to tear it apart. Somewhere between those forces lies a fragile equilibrium that can last for billions of years. The spin of a planet does not emerge out of nowhere. It is inherited. Every world carries the momentum of the cloud it was born from. Long before a planet exists, there is a cold, diffuse disk of gas and dust orbiting a newborn star. Inside that disk, tiny irregularities in movement appear, uneven flows, local eddies, turbulence. These small twists, magnified over time by gravity, evolve into the first stable rotations. When matter begins to collapse inward, a physical rule takes over: the conservation of angular momentum. As the radius of the collapsing region shrinks, the rotation speeds up. The principle is simple. A spinning system that contracts cannot lose its angular momentum, so the spin must accelerate. What begins as a cloud moving slower than walking speed can turn into a planet rotating at tens of thousands of kilometers per hour. This process is not limited to Earth-sized worlds. It happens everywhere in the cosmos. Whether it's a small rocky planet or a massive gas giant, the rule is the same. Collapse leads to rotation. In fact, the spin we observe today in Earth is a remnant of motions that existed 4.5 billion years ago, preserved through the entire history of the solar system. During formation, collisions also play a decisive role. As young planetary embryos sweep through the disk, they collide, merge, and absorb one another. Each impact changes the spin tilting axes, speeding up or slowing down rotation. Earth likely received its current rotation from a giant collision in its early history, the same event that is believed to have formed the Moon. These impacts left permanent fingerprints that still shape the rhythm of our planet's day. Even after formation ends, spin continues to evolve. Tidal interactions with moons or stars can slow rotation over billions of years, like a brake pressed gently but persistently. Yet the core momentum remains. No force erases the original twist completely. Planets may change, cool, or drift, but the spin born in those first moments endures as a silent record of their origin. Not every planet spins in a neat, upright position. Each world carries the history of its collisions, migrations, and tidal interactions, stories written into the tilt of its axis. Earth is tilted by about 23.5 degrees, giving us our cycle of seasons. Mars has a similar tilt, creating seasonal changes familiar in structure, but far harsher in scale. Meanwhile, Uranus spins almost sideways, its axis tilted by more than 90 degrees. Instead of gentle seasons, Uranus experiences years of one hemisphere baking in sunlight, while the other lies in darkness. This extreme variety is not random. In their violent youth, planets frequently collided with other large bodies. Each impact could tilt a rotation axis or even flip it entirely. Earth's tilt likely traces back to one such collision with a Mars-sized body over 4.5 billion years ago. That same impact is thought to have thrown debris into orbit, forming the Moon. Venus may have suffered a different kind of blow. It spins slowly and backward compared to most planets, a retrograde rotation that suggests either an enormous impact or a series of smaller interactions that gradually reversed its spin. Tidal forces also reshape rotation over long timescales. The Moon pulls gently on Earth's oceans, creating tides, but also slowing the planet's rotation over millions of years. The same process works in reverse. Earth's gravity keeps the Moon tidally locked, forcing it to always show the same face. On other worlds, such interactions can be far more extreme, locking entire planets into synchronous rotation, where a day lasts as long as a year. Each axial tilt, each peculiar rhythm of rotation is a clue. It tells astronomers not just how a world moves today, but what happened to it in the distant past. Spin is not just inherited at birth. It is rewritten through time by every collision, every gravitational tug, and every subtle force that shapes the architecture of planetary systems. Every world begins with a turn. From that silent motion, everything else unfolds: climate, air, and the long balance between day and night. The 24-hour rotation of Earth spreads sunlight evenly between day and night, preventing extreme temperature differences. Without this steady rotation, one hemisphere would scorch, while the other froze, leaving only a narrow twilight zone habitable. Venus, with its slow retrograde rotation, offers a glimpse of this imbalance. Temperatures remain blistering hot across its surface, and its thick atmosphere moves in violent circulation patterns to compensate. Rotation also drives atmospheric dynamics. On a spinning planet, rising warm air and descending cool air are deflected by the Coriolis effect, creating global wind belts and weather systems. Earth's trade winds, jet streams, and ocean currents all depend on this invisible steering force. A slower spin would produce sluggish atmospheric circulation, while a faster spin could lead to chaotic, storm-dominated climates, like those seen on Jupiter, where rapid rotation fuels colossal storms that can last centuries. The effects of spin reach beneath the surface too. Earth's rotation works with the motion of molten iron in its core to sustain its magnetic field, a protective shield against charged particles from the sun. If the planet rotated significantly slower, this geodynamo could weaken, exposing the atmosphere to erosion by solar wind. Mars, which spins at a similar rate but lost its internal heat and magnetic field long ago, shows what happens when this protection fades. Its atmosphere thinned, its climate collapsed, and its surface became a frozen desert. Spin in the end is not just a trace of planetary birth, it is a stabilizing engine. It moderates temperature, stirs the atmosphere, and sustains the invisible shields that make a world capable of holding onto its air and water for billions of years. Not all planets rotate at a pace as balanced as Earth. The length of a day can stretch from a few hours to hundreds of days, and that variation reshapes everything from weather to habitability. Jupiter turns once in less than 10 hours. Its rapid spin stretches its equator, amplifies its atmospheric circulation, and fuels immense storms, including the Great Red Spot, a vortex larger than Earth that has raged for centuries. In contrast, Venus needs over 2,800 hours to complete a single rotation. That glacial pace contributes to its hellish surface conditions, where thick clouds trap heat and winds circle the planet at hurricane speeds. Too much spin, and a planet becomes a storm machine, its atmosphere carved into violent jets and endless vortices. Too little, and one side bakes while the other freezes, locked in brutal thermal contrast. Only within a narrow band does rotation steady the climate, giving life a chance to endure. There is a narrow middle ground where rotation stabilizes rather than destabilizes. It is within this range that climates balance, magnetic fields endure, and ecosystems can persist. Earth lies in this window not because it was designed to, but because the physical processes that shaped it placed it here. In the story of planet spin is not just movement. It is a condition for survival. Planetary systems inherit their spin from the swirling disks that birthed them. This shared momentum sets their orbits and rotations in motion, not as an afterthought, but as a natural outcome of their formation. From that single rotation, worlds emerge, each carrying a piece of the original spin. Spin also influences how planets interact with one another. Gravitational tides transfer angular momentum between worlds, gradually slowing some rotations while locking others into resonant patterns. Mercury, for example, is trapped in a 3-to-2 spin-orbit resonance, with the Sun turning 3 times for every 2 orbits. The Moon shows only one face to Earth because its rotation has synchronized with its orbit. Over astronomical time, these exchanges can reshape the rhythm of entire systems. A planet's spin is both a fingerprint of its past and a key to its future. It records the forces that built it, sustains the structures that keep it stable, and slowly evolves under the pull of everything around it. The story of planetary rotation is not static. It is a slow, continuous transformation, one that begins in a swirling cloud and ends in the long silence of gravitational equilibrium. Stars take this principle to a more extreme scale. Here, rotation no longer just shapes a surface, it controls entire stellar interiors. Differential motion between latitudes drives powerful magnetic dynamos, and the resulting stellar winds sculpt planetary systems across astronomical units. This is not a mirror of planetary spin, but an escalation of its consequences. Stellar rotation is inherited from the same collapsing cloud of gas and dust that forms both the star and its surrounding planetary system. As the cloud contracts, the conservation of angular momentum accelerates the spin of the forming protostar. Much like a figure skater spinning faster as they pull their arms in, the protostar speeds up as its radius shrinks. At this early stage, rotation can be far faster than what we observe in mature stars. Over time, stellar winds carry angular momentum away, slowing the surface rotation. Not all stars rotate at the same rate. Massive hot stars can spin many times faster than the Sun, with equatorial velocities exceeding hundreds of kilometers per second. Such rapid rotation flattens their shapes, alters their internal structure, and generates intense magnetic fields. Vega, one of the brightest stars in the night sky, rotates so fast that it is significantly ablate, with its poles hotter and brighter than its equator. At these speeds, even small differences in rotation can have enormous effects on stellar behavior. From here on, think of rotation not as weather but as architecture, the blueprint of stellar systems. Long before a star shines, it spins. The story begins inside a vast molecular cloud, cold and dark, drifting silently between the star. Gravity slowly pulls matter toward denser regions, forming clumps that grow heavier over time. As each clump collapses inward, the conservation of angular momentum ensures that its rotation accelerates. A diffuse region, once barely moving, begins to turn like a massive gyroscope. This is how a protostar is born, not in stillness but in motion. During this phase, the forming star spins far faster than it ever will in its mature life. Because its radius is shrinking rapidly, even a faint initial twist can turn into extreme rotation. At the same time, magnetic fields thread through the collapsing gas, connecting the protostar to the surrounding disk of material. This interaction redistributes angular momentum, transferring part of the spin outward. Without this process, the forming star could spin so fast that centrifugal forces would tear it apart before nuclear fusion ever ignited. The surrounding disk plays a crucial role. As gas spirals inward, it doesn't fall directly onto the star, it lands near the equator, feeding the spin. Meanwhile, powerful magnetic fields act as a brake, carrying excess momentum away in the form of stellar winds and outflows. This balance determines the final rotation rate of the newborn star. If the braking is weak, the star can emerge spinning at dangerous speeds. If it's strong, the rotation slows enough for stability. Different types of stars emerge from this process with different spins. Low-mass stars like the Sun rotate modestly. Massive O and B-type stars, however, often keep more of their angular momentum spinning at speeds that can exceed 200 kilometers per second at the equator. Their shapes flatten their surfaces, heat unevenly, and their behavior becomes more violent and unstable. Spin is not an accessory of star formation. It is one of its defining features. It is imprinted in the very first moments when gas condenses out of a dark cloud, setting the pace for everything the star will become. Stars follow the same rule. Fast spin flattens them. Nearby speed demons like Altair or Vega even show this flattening directly. These structural distortions affect stellar temperature, brightness, and stability. Faster rotation enhances differential motion between layers inside the star, stirring the plasma in powerful internal flows. These flows mix hydrogen and other elements, more efficiently extending the star's lifespan in some cases and accelerating its evolution in others. The balance is delicate. Too much mixing can destabilize the outer layers, amplifying stellar winds and mass loss. Too little, and the star may burn through its fuel unevenly. Rotation also plays a key role in generating magnetic fields. Just as the motion of molten iron inside Earth sustains its magnetic shield, the movement of charged plasma inside a star powers a magnetic dynamo on a far larger scale. Faster spin amplifies this effect, producing stronger and more complex magnetic fields. These fields shape stellar coronae drive flares and sunspots, and accelerate streams of charged particles outward into space. But high spin comes at a cost. As the stellar wind intensifies, it carries angular momentum away, gradually slowing the star's rotation. This spin-down effect is most dramatic in young stars, which can lose a significant fraction of their angular momentum in their first 100 million years. Over time, the star settles into a more stable rhythm, its furious spin tamed by the very energy it produces. In the end, stellar rotation is both a source of power and a self-limiting force. It builds magnetic fields, stirs plasma and shapes stellar life cycles, but it also sows the seeds of its own slowing, ensuring that no star spins at full speed forever. Not all stars rotate alike. The pace of their spin depends on mass, age, composition, and environment. Young stars typically rotate the fastest. In their early life, their magnetic braking is still weak, and they have not yet shed much angular momentum through stellar winds. Observations of young stellar clusters show stars turning with periods of just a few hours. Over time, this rapid spin slows as their magnetic fields grow stronger, and their winds carry away momentum. Mass is another decisive factor. Low-mass stars like the Sun spin at moderate speeds and gradually slow over billions of years. Massive stars, O-type and B-type, rotate at far higher velocities, sometimes exceeding 200 or even 300 kilometers per second at the equator. Their enormous size gives them immense angular momentum, and because they have shorter lifespans, they don't lose much of it before burning out. These stars are often visibly ablate their poles hotter and brighter than their stretched equators. Binary systems can complicate this picture further. When two stars orbit closely, tidal interactions can synchronize their spins with their orbital motion. In extreme cases, they can exchange angular momentum, directly spinning one another up or down. Some stars in close binaries rotate much faster than isolated stars of the same type, driven by gravitational tugs from their companions. Others are slowed, locked into a stable synchronous state where spin and orbit match perfectly. Chemical composition and internal structure also influence rotation. Stars with convective envelopes can generate stronger magnetic fields which accelerate spin down through stellar winds. Stars with radiative envelopes, by contrast, retain their rotation longer. This is why hotter, more massive stars can maintain high spin rates throughout their short but intense lives. By studying stellar rotation across different types, astronomers can reconstruct their histories and forecast their fates. A star spinning rapidly today may be young, massive, or part of a binary system. A slower star may be older, losing its angular momentum with age. Spin in this sense is a kind of cosmic fingerprint unique to each star, yet governed by universal laws. The pace at which a star spins can determine how it lives and how it dies. Inside a star, the distribution of angular momentum influences how energy and material flow between its layers. A rapidly rotating star mixes hydrogen and helium more efficiently, sometimes prolonging its stable burning phase. This internal stirring can delay the depletion of core hydrogen, slightly extending the star's lifetime compared to a similar star spinning more slowly. But the same process can also accelerate instability once the star nears the end of its fuel supply. Fast rotation intensifies stellar winds. Streams of charged particles erupt from the surface, stripping away mass and carrying angular momentum into space. In massive stars, this effect can become extreme. As the outer layers thin, internal pressures rise and the star can shed material at astonishing rates. This mass loss changes not only its spin but also its future evolution. A star that loses enough mass can follow a completely different path to its death, ending its life as a less massive supernova or collapsing into a neutron star rather than a black hole. The same conserved spin that shaped planets also drives stellar lives. Here the stakes are higher. Rotation can help decide how a star evolves, sheds mass, and ends. Rotation then is not merely a chapter in a star's life. It is the thread that connects its birth, its long burning middle age, and its final act. How fast a star spins can be the difference between a quiet fade and a cosmic explosion. A star does not keep its original spin forever. Over time it slows down. This gradual deceleration is called spin down, and it is one of the most reliable indicators of stellar aging. Young stars turn quickly, old stars slow. Magnetic fields couple the star to its wind and bleed away angular momentum, a gentle break that grows weaker with age. Because this slowdown follows a predictable path, astronomers use gyrochronology. Read the period, infer the age, and trace how rotation evolves across stellar lifetimes. Spin down is not the same for every star. Low-mass stars with deep convective envelopes spin down efficiently because their magnetic dynamos are strong. High-mass stars with radiative envelopes lose angular momentum more slowly. Binary systems can also complicate this pattern, as tidal interactions may either slow or maintain the star's rotation depending on the orbital configuration. In this way, spin is more than just a feature of stellar behavior, it's a clock. By reading the rhythm of rotation, astronomers can look backward in time, revealing how long a star has been shining. Every turn of a star is another tick in a cosmic chronometer that began on the day it was born. Not all stars follow the clock. Tight binaries can tidally lock spins and stall the break. Strong or tangled magnetic fields can change the slowdown rate. Mergers can spin up an old star to newborn speeds, and close giant planets can trade momentum with their hosts. These outliers do not break gyrochronology. They calibrate it, revealing where hidden physics reshapes the timeline. We measure stellar spin not by watching the surface, but by reading its light. Spectroscopy broadens the star's absorption lines, showing how fast its surface moves. Photometry tracks rhythmic dips in brightness as star spots turn in and out of view, and interferometry used on nearby speed demons like Altair and Vega directly reveals their oblate shapes. Each method has limits alone, but together they let us map stellar rotation across unimaginable distances. Imagine the sun shrinking to the size of a city but refusing to let go of its spin. What emerges is no ordinary star. It's a whirling core of pure force where gravity and rotation meet at their limits. Carry that same rule one step further. When a stellar core shrinks into a neutron star, rotation is amplified to the extreme hundreds of turns each second. To imagine this transformation, picture the sun shrinking to the size of a city while retaining its spin. The result would be an object rotating dozens or even hundreds of times per second. Many neutron stars actually do exactly that. Some rotate so fast their equatorial speeds reach a significant fraction of the speed of light. This is not theoretical speculation. These rotations have been measured with exquisite precision. The interior of a neutron star is an exotic landscape where atomic structure collapses. Electrons and protons fuse under crushing gravity, leaving behind a super-dense sea of neutrons. A single teaspoon of this material would weigh billions of tons. In such extreme conditions, even a slight change in angular momentum has enormous effects on the star's behavior. Because neutron stars are so compact, their spin is remarkably stable. Unlike the turbulent plasma of ordinary stars, these objects behave more like solid bodies, maintaining their rotation with atomic clock precision. But not all neutron stars spin at the same rate. Some rotate only a few times per second. Others, the fastest, are known as millisecond pulsars, spinning hundreds of times every second, their surfaces racing at speeds far beyond anything possible on a planet or normal star. This is where rotation crosses into the extreme. A neutron star doesn't merely spin fast, it spins with a precision so rigid it defies almost any attempt to slow it. These stellar remnants are nature's perfect gyroscopes, carrying the memory of their former stars in every revolution. Some neutron stars are not silent. As they spin, they sweep powerful beams of electromagnetic radiation through space like a rotating lighthouse. These are pulsar neutron stars with intense magnetic fields and rapid rotations. Their magnetic axis is tilted relative to their rotational axis, so the beams point in a different direction than the spin. As the star turns, the beams sweep across the cosmos. If Earth happens to lie in their path, we detect a regular pulse of radiation with incredible precision. These pulses can arrive hundreds of times per second. Each one corresponds to a single rotation. The fastest pulses, called millisecond pulses, spin at nearly 700 revolutions per second. Their timing stability rivals the most advanced atomic clocks ever built. Astronomers can predict their pulses to within microseconds over years of observation. That precision elevates pulses from curiosities into instruments. Natural beacons scattered across the galaxy, steady enough to measure the fabric of space-time. The physics behind this phenomenon is extreme. The magnetic field of a pulsar can be trillions of times stronger than Earth's. As the neutron star spins, it drags this magnetic field around accelerating charged particles and launching radiation along its magnetic poles. The rotation powers everything. Unlike ordinary stars, pulsars shine not from fusion, but from their spinning energy. Over time, pulsars lose energy as radiation bleeds away angular momentum. Their spin gradually slows, but the process is incredibly stable. Even their spin down follows predictable curves, allowing astronomers to measure their age and internal structure. Some pulsars in binary systems can even be recycled. When they accrete matter from a companion star, the infalling material transfers angular momentum, spinning them up again to even faster speeds. For scientists, pulsars are more than stellar remnants. They are precise clocks, natural laboratories for gravity and quantum physics, and probes of the structure of space-time itself. Each pulse is a tick in a cosmic metronome generated by an object so dense and fast that it tests the very limits of what matter can endure. Although pulsars rotate at extraordinary speeds, their spin is not truly eternal. Over time, they lose energy through radiation and particle outflows, causing a gradual slowdown called pulsar spin down. But this deceleration is so stable, so precisely measurable, that it turns pulsars into some of the most accurate natural timekeepers in the universe. The mechanism is rooted in their powerful magnetic fields. As a pulsar spins, its rotating magnetic dipole emits electromagnetic radiation, carrying away angular momentum. This steady loss acts like a cosmic brake, reducing the rotation rate by a minuscule amount with each passing year. For many pulsars, the decrease in period is only a few nanoseconds per year, barely noticeable yet constant and predictable. This smooth, clock-like slowing allows astronomers to track their age and internal properties with remarkable precision. Some pulsars, particularly millisecond pulsars, are so stable that their timing rivals or even surpasses the best atomic clocks on Earth. Their pulses arrive with deviations of less than a millionth of a second over spans of years. This stability makes them ideal tools for testing fundamental physics. Among all known pulsars, the fastest one ever discovered spins more than 716 times each second. That's faster than a blender blade. Over years, its pulses drift by less than a millionth of a second. That's why pulsars are often called cosmic clocks. They don't just mark time, they let us measure how the universe itself bends and shakes. Their precision allows astronomers to detect faint gravitational waves, map the structure of space-time, and even navigate spacecraft across the galaxy. Each pulse is like a tick of a cosmic metronome, steady, sharp, and relentless. By monitoring tiny variations in the arrival times of these pulses, scientists can probe the curvature of space-time and detect ripples from distant cosmic events, Not all pulsars slow down evenly. Occasionally they experience sudden jumps in rotation rate called glitches. These are thought to arise from the complex internal structure of neutron stars, a solid crust overlaying a superfluid interior. When stress builds and the crust shifts, the stored angular momentum is abruptly released, spinning the star up by a tiny but measurable fraction. These glitches offer rare glimpses into the extreme physics hidden beneath the surface. Despite such events, the long-term spin down remains astonishingly regular. Pulsars are more than relics of stellar death. They are metronomes forged by gravity magnetism and rotation ticking steadily across cosmic time. Their measured deceleration is not just a curiosity, it is a tool for measuring the universe itself. Pulsar precision isn't a mere scientific curiosity, it's a measuring device, a cosmic ruler etched in time. Because their pulses are so regular, pulsars can be used to measure and map the universe with astonishing accuracy. They act as natural beacons, their signals crossing vast distances almost unchanged, carrying timing information that remains precise for years or even decades. One of the most powerful applications is in pulsar timing array experiments. By carefully monitoring dozens of millisecond pulsars across the sky, scientists can detect minute changes in the arrival times of their pulses. These tiny fluctuations are caused by space-time itself stretching and compressing as gravitational waves pass through our galaxy. Unlike ground-based detectors which sense short bursts, pulsar timing arrays are sensitive to ultra-long gravitational waves, ripples produced by colossal events like the merging of supermassive black holes. Pulsars can also serve as a kind of cosmic GPS. Because their locations and pulse rates are well known, a spacecraft equipped with the right instruments could navigate autonomously anywhere in the galaxy by triangulating its position relative to several pulsars. This idea, once theoretical, has already been tested in space through technology demonstrations, showing navigation accuracy down to a few kilometers without any contact with Earth. They are also crucial for testing general relativity. Binary pulsars where a pulsar orbits another star or another pulsar create natural laboratories for gravity. By tracking their pulses, scientists can measure tiny deviations in their orbits, revealing how space-time curves and behaves near extreme masses. These systems have confirmed predictions of Einstein's theory to extraordinary precision. Beyond physics, pulsars offer clues to stellar evolution, galactic structure, and even the distribution of matter in interstellar space. Each pulse must travel through clouds of gas and plasma, and the way it's delayed or distorted reveals properties of the medium it crosses. Pulsars are not simply remnants of stellar death. They are instruments forged by nature, precise enough to explore forces that shape the cosmos itself. Near the hard ceiling, tiny spin-ups no longer look tiny. The equator bulges layers shear, and brief glitches or short flashes can erupt as matter skims off the surface. At these speeds, frame dragging becomes measurable, turning each pulsar into a lab for strong gravity. What we time on Earth are not just pulses, they are stress tests of nuclear matter and space-time run by nature on a millisecond clock. Even here, the equator strains first, the same geometry as planets compressed into a few kilometers, but the details belong to extreme gravity physics. At the very edge, something more dramatic can occur. If the star's mass is high enough, pushing beyond this rotational threshold could cause it to collapse inward, overcoming even the degeneracy pressure of neutrons. The result? A rotating Kerr black hole. This transition would be swift, catastrophic, and irreversible, the last moment where spin belongs to a neutron star before it is absorbed into the curvature of spacetime itself. In these extreme regimes, spin is more than motion. It is a test of the universe's deepest physical laws. Observing neutron stars at the brink gives us a rare chance to watch those laws being pushed to their absolute limit. When a neutron star crosses the threshold where even its degenerate matter can no longer resist gravity, the result is a rotating Kerr black hole. But even the fastest pulsars have a limit. Beyond it, gravity wins. When a spinning neutron star collapses, it doesn't just disappear. Its angular momentum is inherited by something far stranger. A black hole. Here rotation no longer moves matter around an object. It twists space-time itself. Unlike planets or stars, a black hole is not just an object spinning in space. Its rotation is embedded in the geometry of space-time itself. As it turns, it drags the surrounding space-time along with it, a phenomenon known as frame dragging. This effect is so intense near the black hole's surface that nothing can remain still relative to distant space, not even light. A rotating black hole is defined by two key surfaces. The first is the event horizon, the boundary beyond which nothing can escape. The second is the ergosphere, a region just outside the horizon where space-time is dragged faster than any object can resist. In the ergosphere, even light must co-rotate with the black hole. A particle or spacecraft entering this region cannot remain stationary, but it can still escape if it moves in the direction of rotation. This rotation is not a detail, it changes everything. The faster the black hole spins, the more distorted space-time becomes. At extreme spins, the ergosphere swells outward, a region where space-time itself is forced into motion. Here, rotational energy can be tapped through mechanisms like the Penrose process and the Blandford-Znajek effect, launching powerful relativistic jets that shape their host galaxies. This is where a black hole's spin stops being an abstract property and becomes a cosmic engine. This phenomenon is the purest manifestation of frame draggings. Unlike the gentle space-time twisting near a rotating planet, here the effect reaches an extreme. If a spacecraft were to enter the ergosphere and attempt to hover in place using any conceivable thrust, it would fail. The geometry of space-time would give it no choice but to turn. In this region, the concept of standing still ceases to exist. Yet the ergosphere is not a dead end. Unlike the event horizon, it is not a point of no return. Objects can still escape provided they move with the flow of space-time. And because of the way rotation stores energy in this region, it is possible, at least in theory, to extract that energy. This is the basis of the Penrose process, in which a particle entering the ergosphere can split into two, with one fragment falling into the black hole, and the other escaping with more energy than the original. The extra energy comes directly from the black hole's rotation, slowly spinning it down. This concept is not just a theoretical curiosity. It forms the foundation for models of how Blandford-Znajek process launches powerful relativistic jets from the poles of supermassive black holes. As magnetic fields thread through the ergosphere, they tap into its rotational energy, accelerating plasma outward at near-light speeds. These jets are bright enough to be seen across galaxies, marking the presence of spinning black holes billions of light-years away. The ergosphere is a reminder that at the heart of a rotating black hole, motion is no longer optional. It is built into the very geometry of existence, a cosmic whirlpool, where space and time themselves are forced to turn. Measuring the spin of a Kerr black hole may sound impossible after all. Nothing can escape its event horizon, not even light. But rotation leaves fingerprints on the space around it, and with the right instruments, those imprints can be read. Today, astronomers use several powerful methods to determine how fast a black hole spins, turning invisible motion into measurable numbers. One of the most important techniques involves X-ray spectroscopy. When gas spirals into a black hole, it forms an accretion disk heating to tens of millions of degrees and emitting intense X-rays. As these X-rays pass through the warped space-time near the event horizon, their energy is shifted and their spectral lines are broadened asymmetrically. By analysing this relativistic broadening, scientists can determine how close the inner edge of the disk lies to the black hole, and that distance depends directly on spin. A faster spin allows the disk to extend closer to the horizon, producing a more extreme signature. Another method comes from timing. As matter orbits near the black hole, it can produce rapid fluctuations in brightness called quasi-periodic oscillations. These oscillations arise from the innermost stable circular orbits, which are determined by the black hole's rotation. By measuring these frequencies, astronomers can infer how fast the black hole is spinning. For the most massive black holes, a newer window has opened: gravitational waves. When two black holes merge, their spins influence the shape of the wave signal, detected by observatories like LIGO Scientific Collaboration and Virgo Collaboration. By carefully modelling these waveforms, scientists can extract information about the spin of each black hole before and after the collision. This has already provided some of the most precise measurements of black hole rotation in the universe. And then there is the most direct view yet: the silhouette of a spinning black hole. Observations of M87 and Sagittarius AM by Event Horizon telescope revealed ring-like images whose asymmetry betrays their spin. Light bending around a rotating black hole is not the same in every direction, and that subtle difference can be measured. We cannot see a black hole spinning, but through its light, its shadows, and the ripples it sends through space-time, its rotation speaks clearly across billions of light years. Even a Kerr black hole cannot spin without limit. Its maximum rotation is set by a boundary known as the extremal spin limit. In this state, the black hole's spin parameter, expressed as the ratio of its angular momentum to its mass, reaches a value of 1. This represents the theoretical maximum allowed by general relativity. A black hole rotating so fast that its event horizon and ergosphere merge at the poles, and the geometry of space-time becomes as twisted as the laws of physics will allow. If the black hole were to somehow exceed this limit, the equations describing its structure would break down, and the event horizon would no longer exist. That would create what physicists call a naked singularity, a point of infinite density exposed to the universe. Such an object would violate the cosmic censorship conjecture, which states that singularities are always hidden behind horizons. So far, no observation has revealed a black hole exceeding this bound. It appears to be one of nature's strictest rules. Approaching this limit has profound consequences. As the spin parameter climbs toward 1, the innermost stable circular orbit moves closer to the event horizon. Matter in the accretion disk can plunge deeper into the gravitational well heating to even higher energies and producing intense X-ray and gamma-ray emissions. Frame dragging grows extreme, forcing space-time itself into a relentless whirl. These conditions are among the most violent environments known. Interestingly, astrophysical black holes are often found spinning rapidly but not perfectly maximally. Processes like accretion and mergers can spin them up, but gravitational radiation and magnetic interactions push back, preventing them from reaching the exact extremal state. This natural balance keeps their spin just below the theoretical ceilings. The extremal spin limit is a line the universe does not cross. It marks the edge of what spacetime can sustain before its own structure gives way. Studying black holes that skirt this boundary offers one of the clearest views into where Einstein's theory holds and where new physics may begin. Close to a Kerr black hole spin is not simply a property of the object itself, it dominates everything around it. As any particle or beam of light approaches the region near the event horizon, it's forced to follow the swirling flow of space-time. The closer it gets, the stronger the drag becomes. At the boundary of the ergosphere, even a photon moving against the rotation cannot escape being carried along. This intense frame dragging distorts the structure of the surrounding region. Light emitted from matter near the black hole is not just bent, but bent unevenly, producing an asymmetric halo. On the side, rotating toward us, photons are boosted to higher energies through relativistic beaming, creating a brighter, bluer arc. On the opposite side, light is stretched to lower energies and dimmed. This is why images of Stevenson captured by Event Horizon Telescope show a lopsided ring rather than a perfect circle. We are seeing the imprint of spin. This asymmetry also affects matter. Gas orbiting close to the black hole experiences enormous velocity gradients with inner regions moving at relativistic speeds. Shock fronts, magnetic fields, and shear flows combine to produce violent energy releases. These interactions feed the black hole's accretion disk and in some cases power the enormous relativistic jets that extend far beyond the host galaxy. Spin sculpts the very geometry of this space. The closer an object moves toward the black hole, the less its motion is governed by its own inertia, and the more it is governed by the rotation of space-time itself. The innermost stable orbit shrinks with increasing spin, allowing matter to approach closer heat more intensely and radiate more energy before plunging inward. The region near a spinning black hole is not passive space. It is a dynamic, twisted structure where geometry, light and motion are inseparable, a place where rotation becomes the architecture of reality itself. A rapidly spinning Kerr black hole is not just a passive object warping space-time, it is a colossal reservoir of rotational energy. Through its interaction with magnetic fields and surrounding plasma, that energy can be tapped and released into the universe in astonishing ways. In fact, some of the most luminous and violent phenomena ever observed owe their power to spin. The most dramatic example is the formation of relativistic jets. Narrow beams of plasma accelerated to nearly the speed of light and launched along the black hole's rotational axis. These jets are thought to be powered by the Blandford-Znaiec process, in which magnetic field lines anchored in the accretion disk thread through the ergosphere. As the black hole spins, it twists these field lines, pumping energy outward. What emerges are jets that can extend for thousands or even millions of light years, shaping their host galaxies and lighting up the cosmos in radio X-ray and gamma-ray wavelengths. Unlike ordinary explosions, this process can sustain itself for millions of years. The rotational energy of a supermassive black hole is vast, often exceeding the total energy of supernovae by many orders of magnitude. Even tapping a small fraction of it can drive structures on a galactic scale. Observations of active galactic nuclei show that the brightest and most powerful jets are often associated with black holes spinning close to the extremal spin limit. Spin also amplifies high-energy radiation. As gas in the accretion disk falls inward, it reaches higher orbital velocities the closer it gets to the event horizon. For a rapidly rotating black hole, the innermost stable circular orbit lies deeper in the gravitational well, allowing the disk to heat to tens or even hundreds of millions of degrees. This produces intense X-ray and gamma-ray emissions detectable across vast distances. In essence, spin turns black holes from silent gravitational traps into engines of cosmic activity. It is a source of power capable of shaping galaxies, regulating star formation, and lighting up the distant universe. But the story doesn't end here. The same spin that fuels black holes also shapes their homes. Jets launched from their poles pierce through interstellar space, stirring and heating entire regions of gas. Over millions of years, this rotation leaves fingerprints on the galaxies themselves, vast star cities turning slowly in the dark. Spin does not end with planets, stars, or even black holes. On much larger scales, entire galaxies rotate. The Milky Way completes one full rotation in roughly 200 million years. Though this is far slower than the rotation of a star or planet, the scale is so vast that the outer edge of the galaxy travels at hundreds of kilometers per second. On a galactic scale, rotation stops being the motion of single bodies and becomes the choreography of billions of stars, gas clouds, and dark matter. The flattened disks and spiral arms we see today are not just the result of centrifugal balance. They are fossil records of how angular momentum was distributed when the universe was young. Dark matter halos hold these systems together, shaping their rotation curves and stabilizing their structure. Over cosmic time, this dance determines not only a galaxy's shape, but also its star formation history, its mergers, and its eventual fate. Galaxies are far too vast for us to watch them complete a single turn. A full rotation of the Milky Way takes hundreds of millions of years. Instead of direct observation, astronomers detect spin by reading its imprint on light, just as they do for stars, but on a much grander scale. One of the most powerful tools is Doppler shift. As different parts of a galaxy rotate, the side moving toward us shifts the light of its stars and gas slightly toward the blue, while the side moving away shifts toward the red. By mapping these shifts across the galaxy, astronomers can build a rotation curve, a plot of orbital velocity versus distance from the galactic center. These curves reveal not just that galaxies rotate, but how their rotation speed changes with radius. Early observations of spiral galaxies delivered a stunning surprise. Instead of slowing down at large distances as expected if most of the mass were concentrated near the center, the outer stars continued to move at nearly constant speed. This flatness of the rotation curves led to one of the most important discoveries in modern astrophysics: the presence of dark matter. Only by invoking vast invisible halos of mass could these motions be explained. Neutral hydrogen gas abundant in galactic disks has been a key tracer in these studies. Using radio telescopes to observe the 21 Centaur line of hydrogen, astronomers can map rotation well beyond the visible edge of the galaxy. This reveals the full extent of the dark matter halo stretching far beyond the luminous disk. High-resolution spectroscopy also allows measurements of rotation in distant galaxies billions of light-years away. Even when these galaxies are mere smudges of light, their Doppler-shifted spectra carry information about how they spin. Through such techniques, astronomers have built a statistical picture of galactic rotation across cosmic time, showing how spin evolves as galaxies grow and merge. In essence, light itself is the language of motion. By listening to the Doppler whispers of distant galaxies, we can watch their colossal silent rotations unfold across billions of years. The way a galaxy spins is not random. Its rotation is deeply connected to its mass, shape, and evolutionary history. One of the most fundamental relationships in astronomy is the Tully-Fisher relation, which links a spiral galaxy's rotational velocity to its total luminosity, and therefore its mass. The faster a galaxy rotates, the more massive it tends to be. This correlation spans across countless systems, from modest spiral galaxies to giant star cities containing hundreds of billions of suns. On the scale of entire galaxies, rotation stops being the motion of single bodies and becomes the choreography of billions of stars, gas clouds, and dark matter. The flattened disks and spiral arms we see today are not just the result of centrifugal balance. They are fossil records of how angular momentum was distributed when the universe was young. Dark matter halos hold these systems together, shaping their rotation curves and stabilizing their structure. Over cosmic time, this dance determines not only a galaxy's shape but also its star formation history, its mergers, and its eventual fate. Galaxies are not isolated dancers in space. They live within the cosmic web, constantly moving, tugging, and sometimes colliding with one another. These encounters are among the most powerful events in galactic evolution, and spin lies at the heart of the transformation they bring. When two galaxies approach, their gravitational fields begin to interact long before they physically touch. Tidal forces twist their disks, pulling out long streams of stars and gas. This exchange can alter their angular momentum dramatically. In some encounters, spin is amplified. Gas is funneled inward, the disk tightens, and rotational velocity increases. In others, spin is disrupted. Stars are scattered, orbits become chaotic, and the once coherent rotation weakens or disappears. Major mergers, collisions between galaxies of comparable mass, can erase disk structures entirely. When two spiral galaxies merge, their spins often cancel or reorient, producing a new elliptical galaxy with little or no net rotation. The random motion of stars replaces the elegant swirl of a disk. This process is a cornerstone of modern galaxy formation theory, explaining why many massive galaxies observed today are ellipticals born from ancient mergers. Minor mergers, where a large galaxy absorbs a smaller one, can have subtler but lasting effects. They can tilt or warp the disk, inject fresh angular momentum, or create counter-rotating structures. Some galaxies contain nested disks spinning in opposite directions, fossil records of such past interactions. Even close flybys can alter spin without a direct collision. Tidal torques during near passes can twist disks, trigger bursts of star formation, and shift rotational axes. Over cosmic time, these interactions accumulate, gradually reshaping a galaxy's spin history. A galaxy's rotation, then, is not just a relic of its birth. It is a living record of everything that has happened to it. Every encounter, every merger, every subtle gravitational whisper written into its spin. The spin of a galaxy is not entirely its own. Across cosmic distances, galaxies are connected by the cosmic web, an immense network of filaments and voids that shapes how matter flows through the universe. This structure doesn't just dictate where galaxies form, it can influence the direction of their spin. Over the last 2 decades, astronomers have found compelling evidence that galactic rotation is often aligned with these cosmic filaments. The story begins with the early tidal torques that set galaxies spinning in the first place. These torques are not random. They arise from the uneven gravitational pull of nearby structures as proto-galaxies collapse. Because the cosmic web has a well-defined geometry, these torques tend to orient galaxies in preferred directions. Spiral galaxies, for example, often have their spin axes aligned along the filaments they inhabit. More massive galaxies, especially ellipticals, may have their spins oriented perpendicular to the filaments, reflecting their more violent merger histories. Cosmological simulations have reproduced these patterns. In large-scale simulations of structure formation, galaxies naturally inherit angular momentum from the flows of matter streaming through filaments. These streams act like cosmic rivers, imparting spin as they feed gas and dark matter into growing halos. Observations using surveys such as Sloan Digital Sky Survey have confirmed these alignments, statistically showing that spin orientation is not random, but shaped by the environment. This alignment is subtle. It does not mean every galaxy spins perfectly in the same direction, but the overall pattern emerges clearly across millions of galaxies. In denser regions where mergers are frequent, these alignments weaken. In quieter filaments, they can persist for billions of years, preserving the memory of the universe's earliest motions. In this way, the spin of a single galaxy is like the stroke of a much larger cosmic brush. Its orientation encodes not only its own history, but also the geometry of the universe itself. Galactic spin is not static. It evolves over billions of years, tracing the changing flow of matter in the universe itself. In the early cosmos, shortly after the Big Bang, galaxies were small, irregular and turbulent. Their spin was weak-shaped primarily by the tidal torques that arose during their collapse. But as time passed, structures grew larger, flows became more organized, and galactic rotation strengthened and stabilized. At redshifts above 2, when the universe was less than 3 billion years old, most galaxies were chaotic. Gas flowed in from multiple directions, and frequent mergers scrambled their angular momentum. Their disks were clumpy and thick with rapid, unstable star formation. Spin at this stage was fragile. It could grow through smooth inflows or vanish in a single merger event. By redshift 1, the picture changed. The cosmic web had matured and gas streams flowing along filaments became more coherent. Galaxies began to settle into thin rotating disks. Their rotation curves grew stable. Their spin axes aligned more consistently with their environment. Star formation shifted from violent bursts to steadier patterns, and the rotation of galaxies started to resemble what we see today. In the present-day universe, galactic spin is more resilient but still dynamic. Mergers are less frequent than in the early cosmos, but when they occur, they can still dramatically reshape rotation. Meanwhile, secular processes slow internal changes, gently redistribute angular momentum through bars, spiral arms, and interactions with dark matter halos. The cosmic trend is clear. Spin emerges from chaos and matures into order. What begins as a faint twist in primordial gas grows into the majestic rotation of entire star systems. And although each galaxy carries its unique spin history together, they reflect the evolving architecture of the universe itself. Not all galaxies follow the smooth, predictable patterns of spin seen in typical spirals. Some rotate at astonishing speeds while others barely spin at all. These outliers offer unique insights into how angular momentum is gained, lost, or redistributed over cosmic time. On one end of the spectrum are high-spin systems, massive thin disk galaxies with rotation velocities exceeding 300 kilometers per second. These extreme rotators are often rich in dark matter, which stabilizes their disks and allows them to maintain rapid ordered motion. Their thin extended spiral arms and sharply rising rotation curves make them some of the most dynamically coherent structures in the cosmos. Examples include giant spirals like UGC 125591, one of the fastest known spinning galaxies. At the opposite extreme lie ultra-diffuse and elliptical galaxies with low or even negligible net rotation. Some of these systems, such as those in dense cluster environments, have had their angular momentum stripped away through repeated mergers and tidal interactions. Others may have formed through processes that never allowed a strong disk to emerge. Their stars move in random orbits, producing rounder, puffier structures that lack the graceful swirl of spirals. Intermediate cases reveal even stranger behavior. Some galaxies possess counter-rotating disks, inner and outer regions spinning in opposite directions. These are often signatures of past mergers or gas accretion from misaligned filaments. Others exhibit warped or twisted spin axes, fossil records of long-past interactions. By studying these outliers, astronomers can test the limits of galaxy formation models. High-spin galaxies show how efficiently angular momentum can be preserved and amplified, while low-spin systems reveal how it can be erased. Together they outline the full spectrum of galactic spin evolution, from graceful cosmic whirlpools to quiet, disordered swarms of stars. The way a galaxy spins doesn't just describe its motion, it shapes its entire internal life. Spin controls how gas flows, how stars form, and how energy moves through the system. Fast rotation can act like a stabilizing skeleton, while slow or chaotic spin can turn a galaxy into a furnace of rapid, explosive starbirth. In high-spin disk galaxies, centrifugal force balances gravity across the disk. This prevents gas from collapsing too quickly, regulating star formation into a steady long-term process. These galaxies tend to have thin disks, well-defined spiral arms, and extended star-forming regions. Over billions of years, this gentle, controlled star formation builds stable, structured stellar populations. Low-spin galaxies tell a different story. When rotation is weak, gravity dominates. Gas can clump together more easily, triggering intense bursts of star formation. These starbursts consume gas rapidly and generate powerful winds driven by supernovae and stellar radiation. Such feedback can expel material from the galaxy, entirely suppressing future star formation and altering its angular momentum. Spin also affects how galaxies exchange gas with their environment. Rapidly rotating disks can sustain cold, extended gas reservoirs, allowing them to keep forming stars for billions of years. Slowly rotating or disturbed systems, by contrast, often lose gas more easily to feedback or tidal stripping, leading to early quenching. Feedback in turn can reshape spin. Outflows driven by stellar winds or central supermassive black holes can remove low angular momentum gas from the center, leaving behind material with higher spin. Over time, this can rebuild or even enhance disk structure, creating a feedback loop between star formation and rotation. Spin and star formation are thus deeply intertwined. One governs the flow of matter, the other sculpts the galaxy's future. This quiet interplay explains why some galaxies shine for billions of years while others burn out in a cosmic flash. At the heart of most galaxies lies a supermassive black hole weighing millions to billions of times more than the Sun. Though tiny compared to the full size of the galaxy, this central object plays a profound role in how the entire system evolves, and its relationship with galactic spin is intimate and complex. In rotating disk galaxies, gas naturally flows toward the center over cosmic time. This inflow feeds the black hole and in doing so transfers angular momentum. The geometry and orientation of this inflowing gas are often set by the galaxy's large-scale spin. If the disk is stable and well aligned, the black hole accretes steadily spinning up as it consumes rotating material. This process can drive the black hole toward the extremal spin limit, making it a powerful energy source. But the influence runs both ways. A rapidly spinning black hole can generate outflows and relativistic jets that extend far beyond the galactic nucleus. These jets can heat and disperse surrounding gas, altering the supply of star-forming material and modifying the galaxy's angular momentum distribution. In some cases, powerful feedback from the black hole can shut down star formation altogether, a process thought to shape the fate of massive galaxies. Spin misalignments add another layer of complexity. If the inflowing gas is tilted relative to the galaxy's main rotation axis, the black hole's spin may become misaligned with the host disk. Over time, accretion can realign the two, or repeated misaligned inflows can keep the system chaotic. Observations of warped nuclear disks and bent jets reveal that such misalignments are common. This dynamic relationship, galaxy feeding its black hole and the black hole reshaping its galaxy, is one of the key engines of cosmic evolution. Angular momentum flows in both directions, linking the smallest and largest structures in the galactic system through spin. Spin doesn't stop at the level of galaxies. On scales of millions of light years, entire clusters of galaxies and even superclusters exhibit coherent motions that hint at large-scale angular momentum. While these structures don't rotate in the same way as solid bodies, their member galaxies often show preferred directions of motion, shaped by gravity and the cosmic web itself. In a galaxy cluster, hundreds or thousands of galaxies orbit within a massive dark matter halo. Over billions of years, as the cluster assembles through mergers and accretion, tidal torques can impart a net spin to the entire system. This can manifest as a slight but measurable preference for galaxies to orbit around a common axis. Observations of some massive clusters reveal velocity gradients across their structures, signatures of slow, large-scale rotation. Superclusters, the largest gravitationally bound structures in the universe, may also carry traces of spin. In these immense formations, such as Laniakea supercluster galaxies and clusters, flow along filamentary highways converging toward gravitational centers. Simulations suggest that these flows can contain rotational components, as the cosmic web twists under its own gravity. This rotation is subtle, but over billions of years, even a gentle cosmic whirl can shape how structures grow and merge. Measuring spin on these scales is extraordinarily difficult. The motions are slow, often just a few tens of kilometers per second over millions of light years, and easily masked by random velocities. But with large spectroscopic surveys and improved simulations, astronomers are beginning to detect these patterns more clearly. Evidence of cluster-scale rotation is now emerging as a frontier of cosmology. The fact that spin persists on such vast scales is a profound reminder. The same physical principles that spin planets and stars also shape the largest structures in the universe. Angular momentum is not just local, it is a cosmic language written into the architecture of everything. The spin we observe today, from planets to galaxies to superclusters, began long before stars or galaxies existed. Its roots reach all the way back to the very earliest moments after the Big Bang. In that young, expanding universe, there were no rotating disks, no stars, no structured flows. But there were tiny fluctuations, quantum ripples frozen into the fabric of spacetime itself. These fluctuations gave rise to regions of slightly higher and lower density. Under gravity, the denser regions grew, eventually collapsing to form the first cosmic structures. But crucially, these collapses were not perfectly symmetrical. Neighbouring overdensities pulled on one another, creating tidal torques that imparted the first angular momentum to forming halos. This mechanism, described by tidal torque theory, seeded the spin of everything that would follow. The early universe was also turbulent on large scales. Gas and dark matter flowed along filamentary channels that would become the cosmic web. These flows carried angular momentum, twisting forming structures into slow, vast rotations. Even at this stage, the patterns of spin were already correlated with the geometry of the universe, setting the stage for the alignments astronomers observe billions of years later. Unlike many other cosmic properties, angular momentum is hard to erase. Collisions can redistribute it, and gravitational interactions can change its direction, but its total amount is largely conserved. This is why the faint tidal tugs that existed when the universe was only a few million years old still shape the spins of galaxies today. In this sense, every rotation we observe, every turning star, swirling disk and spinning galaxy cluster, is a fossil trace of the early universe. Spin is not an afterthought of cosmic structure, it is a direct descendant of the universe's birth. At every scale, from planets to galaxies to superclusters, rotation is governed by one of the most fundamental laws in physics, the conservation of angular momentum. This principle ensures that once a system begins to spin, it will keep spinning unless acted upon by external forces. Across cosmic time, this simple rule creates some of the most spectacular structures in the universe. When a gas cloud collapses under its own gravity, its radius shrinks dramatically, but because its angular momentum remains constant, its spin speeds up just as an ice skater spins faster by pulling in their arms. This is why rotating disks form naturally during the birth of stars, planets and galaxies. Rotation isn't something added later, it's built into the collapse itself. Angular momentum can also be transferred, redistributed or redirected. In galactic disks, for example, spiral arms, bars and magnetic fields can act as conveyor belts, moving angular momentum outward while gas flows inward. This transfer allows central black holes to grow while the disk maintains its stability. In galaxy mergers, angular momenta from both systems combine in complex ways, producing new spin axes or even cancelling each other out entirely. On larger scales, cosmic flows transport angular momentum between halos through tidal torques. The cosmic web is not just a static skeleton of matter. It's a dynamic network through which angular momentum circulates over billions of years. This flow is why spin alignments can persist across vast distances, and why individual galaxies still remember the geometry of their birth environment. Even though collisions, feedback and turbulence can change how spin is distributed, the total angular momentum of the universe remains effectively constant. It's not lost, only reshaped. Every merger, every collapsing cloud, every jet or outflow is part of a grand redistribution. Spin is, in a sense, the universe's way of keeping track of its own history. It's a cosmic ledger, one that records not just where matter is, but how it moves, and how it has always moved since the beginning of time. Throughout the universe, gravity and spin are locked in a constant, delicate contest. Gravity pulls matter inward, striving to collapse it into denser structures. Spin through centrifugal force pushes outward, resisting that collapse. The shape, structure and evolution of nearly every astrophysical object emerge from this interplay. In a star-forming cloud, for example, gravity causes the gas to contract, but as the cloud spins faster, centrifugal support builds up. This halts collapse along the rotation axis, flattening the cloud into a disk. Planets form within these disks because rotation stabilizes the structure long enough for material to coalesce. Without spin, many of these systems would collapse directly into a single object, leaving no room for worlds to form. On galactic scales, the same principle applies. Rotation keeps spiral galaxies from collapsing entirely into compact spheroids. Their disks are not static structures, but dynamic balances between gravitational attraction and rotational support. If their spin were lower, they would be more prone to rapid collapse and violent bursts of star formation, or even structural instability. Spin can also influence how matter accretes onto massive structures. In galaxy clusters and superclusters, rotational components can slow the rate of inward collapse, shaping the final distribution of galaxies and gas. In cosmological simulations, regions with higher angular momentum often produce more extended, less centrally concentrated structures. This competition extends to the most extreme environments. Near-Kerr black holes spin warp spacetime so strongly that it alters how matter falls inward. Frame dragging and centrifugal effects combine with gravity to create complex orbital structures, from stable accretion disks to high-energy relativistic jets. Gravity gives structure its weight, spin gives it shape. The balance between these two fundamental forces determines whether matter becomes a flattened disk, a sprawling galaxy, a rotating star, or a dense collapsing core. It is this balance that has carved the visible universe into the intricate spinning patterns we observe today. The universe did not grow chaotically. Its structure, from galaxies to clusters to the cosmic web, evolved in a way shaped not only by gravity, but also by angular momentum. Cosmic expansion stretches space outward. Gravity pulls matter inward, and spin provides the third ingredient. Rotational motion that resists collapse redistributes energy and stabilizes structures over time. In the early universe, when density fluctuations first grew, regions with higher angular momentum collapse more slowly. Spin acted as a brake, delaying the formation of compact structures and allowing matter to settle into extended rotating systems. This is why spiral galaxies tend to form later than elliptical galaxies. Their higher spin made their collapse more gradual, giving them time to assemble ordered disks. Spin also shapes how structures evolve after they form. Rotating galaxies are more resistant to violent internal instabilities. Their ordered motion channels energy and mass into stable patterns that can persist for billions of years. In contrast, low-spin systems are more easily destabilized by mergers or gravitational interactions, often evolving into spheroidal or irregular forms. At larger scales, spin affects the assembly of galaxy clusters and superclusters. Rotational components in their formation can slow and fall, broaden their shapes, and influence the paths of merging substructures. These effects are subtle but significant, producing the wide variety of cluster morphologies observed in the present-day universe. This regulatory role of spin may even extend to the distribution of dark matter. Simulations suggest that regions with higher angular momentum develop less concentrated halos, while low-spin regions produce denser, more compact cores. This difference affects everything from galaxy rotation curves to star formation rates. Spin is in essence a kind of cosmic moderator. It doesn't overpower gravity, but it shapes its work, smoothing, slowing, and redistributing matter as the universe builds itself. Without spin, the cosmos would be a denser, more chaotic place. With it, structures grow not just by collapsing, but by turning into existence. For most of human history, cosmic spin was invisible, a vast silent motion unfolding on timescales far beyond our perception. But with modern telescopes and large-scale cosmological simulations, astronomers are now uncovering how angular momentum is woven into the architecture of the cosmic web itself. The universe is not randomly structured. Galaxies are arranged along filamentary highways of dark matter and gas, with clusters forming at their intersections and voids in between. Simulations of structure formation show that as matter flows along these filaments, it twists. This twisting naturally imparts spin to forming halos, and these spins tend to align with the filaments that birthed them. This alignment is subtle but widespread, an invisible choreography extending across hundreds of millions of light years. Observations are beginning to confirm these patterns. Surveys like the Sloan Digital Sky Survey and Dark Energy Spectroscopic Instrument have mapped millions of galaxies, allowing astronomers to statistically detect preferred orientations of their spin axes. When analysed in bulk, these alignments trace the filaments of the cosmic web, revealing a hidden layer of order beneath what once seemed random. Cosmological simulations push even deeper. They show that these patterns evolve with time. Early galaxies align more strongly with filaments, while later mergers and interactions gradually scatter their orientations. High-spin galaxies tend to retain these alignments longer, while low-spin systems lose them quickly, becoming dynamically noisy as their histories grow more complex. This emerging picture is transforming how we understand cosmic structure. Spin is more than motion. It's a signature etched into everything from planets to galaxies, from the smallest cores to the cosmic web itself. It carries the memory of how the universe built itself and how it moves still. Every turn is a trace, every rotation a record, and when we learn to read that record, we see the hidden structure of the cosmos itself. In short, spin is not merely an outcome, it is evidence. It carries encoded information about the invisible forces shaping the cosmos. By decoding this pattern, we can peer deeper into the nature of dark matter, dark energy, and gravity itself. The study of cosmic spin is entering a new era. For decades, astronomers could only measure the rotation of nearby galaxies in limited numbers, but with the next generation of telescopes and surveys, spin will become a precision cosmological tool mapped across billions of light years with unprecedented detail. A major leap will come from Vera C, Rubin Observatory and its legacy survey of space and time. This ambitious project will observe the entire southern sky over a decade, tracking billions of galaxies and their orientations. By combining their shapes, Doppler signatures and alignments, scientists will be able to reconstruct the spin field of the cosmic web itself. Meanwhile, Euclid and Nancy Grace Roman Space Telescope will extend this map deep into the early universe. Their high-resolution imaging and spectroscopy will reveal how spin evolved across cosmic time, from chaotic, early proto-galaxies to the structured disks of today. This will allow cosmologists to test models of tidal torque dark matter and large-scale structure formation with exquisite precision. Radio astronomy will also play a key role. The square-kilometre array, once completed, will map the 21 centimeter line of neutral hydrogen in billions of galaxies. This will provide direct velocity measurements far beyond the optical range, filling in the rotation curves of distant systems and exposing spin signatures at unprecedented scales. In parallel, high-resolution cosmological simulations are advancing rapidly. They now incorporate baryonic physics feedback and magnetic fields with remarkable accuracy. When combined with upcoming surveys, these simulations will allow scientists to not just detect spin but to decode it, tracing its origin and evolution back to the universe's earliest moments. For the first time in history, we are approaching the point where the rotation of the cosmos itself can be mapped and understood. What was once invisible, the silent turning of the universe, will soon become measurable, structured and deeply revealing. Everywhere we look, the universe is turning. Planets orbit and rotate. Stars spin on their axes. Neutron stars and pulsars whirl hundreds of times per second. Black holes twist spacetime itself. Galaxies rotate in vast, elegant disks. Even clusters and superclusters carry traces of angular momentum. This is no coincidence. Spin is not a local quirk, it is a universal pattern. One reason for its ubiquity lies in the conservation of angular momentum. Once set in motion, rotation persists unless acted upon by external forces. In a cosmos born from an expanding, uneven distribution of matter, tidal torques were inevitable. Those early twists were amplified by gravity, locked into forming structures, and preserved across billions of years. Another reason is stability. Spin acts as a counterweight to collapse. It flattens clouds into disks, stabilizes galactic structures, and regulates the pace of star formation. Without rotation, the universe might still have formed stars and galaxies, but their shapes and dynamics would have been radically different. The graceful spirals and long-lived planetary systems we know today likely wouldn't exist. Spin also connects scales that seem unrelated. The same physics that governs a rotating planet governs the rotation of galaxies and black holes. It's a bridge between the very small and the unimaginably vast, a physical principle that applies as smoothly to an accretion disk as it does to a cosmic filament, and beyond its physical roll spin is deeply revealing. It encodes the memory of the universe's birth, carrying the fingerprints of primordial fluctuations, tidal forces, and cosmic evolution. By studying spin, we're not just describing motion, we are reading the history written into the structure of reality itself. The turning of the universe is not just a phenomenon, it is a signature, a quiet, enduring rhythm underlying everything that exists. From the quiet turning of a planet to the twisting of entire galaxy clusters, spin is the common thread connecting all cosmic structures. It begins with a simple rule, the conservation of angular momentum, and unfolds into the architecture of the universe itself. What seems like an ordinary property of motion is in truth a hidden scaffold that shapes how everything forms, evolves, and endures. At the smallest scales, spin stabilizes star-forming disks and creates the conditions for planetary systems to exist. It determines how worlds tilt, how climates behave, and how long they remain stable. At stellar scales, rotation controls lifespans, powers gamma-ray bursts, and defines the destinies of stars as they collapse into neutron stars or Kerr black holes. At galactic scales, spin sculpts the disks that hold hundreds of billions of stars, regulates star formation, and drives feedback loops between galaxies and their central supermassive black holes. It explains why galaxies take on their elegant spiral shapes, how they interact with one another, and how they retain memory of the cosmic web that shaped them. On even grander scales, spin threads through galaxy clusters and superclusters, aligning with the cosmic web that emerged from primordial fluctuations after the Big Bang. It reflects how tidal torques set everything in motion, and how that motion has been conserved across billions of years. This continuity is extraordinary. The same physical principle that governs the spin of an ice skater governs the dynamics of a galaxy. What differs is only the scale. Across light years and epochs, the universe is not static. It is endlessly turning, carrying the echo of its own beginning in every revolution. The universe has no conductor. No hand directs the motion of stars, planets, or galaxies, and yet everything turns. From the first faint tidal torques that twisted ancient clouds of gas to the spiraling disks of galaxies, today rotation has been a quiet, constant rhythm in the cosmic symphony. It is the universe's heartbeat, steady, silent, and unbroken across time. Spin is memory. Every revolution is a record of the moment when structure first took shape, preserved not in stone or dust, but in motion itself. It is a remnant of the earliest gravitational whispers, amplified and carried forward for billions of years. Long after stars fade, long after galaxies drift apart, that primordial momentum will still be etched into the architecture of space. It is also power. The spin of a Kerr black hole can light up galaxies. The rotation of galaxies regulates star formation, sustaining cosmic structures for eons. Even the slow turning of galaxy clusters carries the imprint of the universe's grand design. Spin doesn't merely accompany cosmic evolution, it drives it. And finally, spin is unity. The same physical law governs the turn of a planet and the rotation of a supercluster. A single thread stretches from the whirl of dust in a protoplanetary disk to the twisting filaments of the cosmic web. One principle written to everything. Long after we're gone, the universe will keep spinning. Not out of purpose, but because it must. Because from the very beginning, when time itself was young, the cosmos was set in motion, and it has never stopped turning. Right now, as you sit here, you are falling. Not down, not up, but through space itself. Our planet is not standing still. It's plunging through the darkness at nearly 30 kilometers every second, falling endlessly around the sun. The sun too is falling, dragged through the galaxy toward an invisible point far away. A gravitational well so massive it bends the motion of hundreds of billions of stars. Every planet, every moon, every galaxy is caught in the same silent descent. We call it orbit. We call it motion, but beneath every path lies the same truth. Everything is falling. Gravity is not just a force that pulls apples from trees. It is the architect of the universe. It sculpts the paths of worlds, bends the flow of time, and decides where galaxies live, where stars are born, and where they die. But why does everything fall? Fall into what if there's no down in space? And how can something fall forever without ever hitting the ground? To answer that, we have to peel back everything we think we know about gravity, because this isn't just a story about a force. This is the story of the hidden current that drives the entire cosmos, a current we are all caught in, a current we can never escape. The universe doesn't stand still, it falls. When we think of falling, we imagine something simple, a rock slipping from a hand, a leaf drifting to the ground, an apple letting go of its branch. But that's only the smallest piece of a much larger truth. Falling is not just what happens when something goes down, it's what happens when something follows its natural path through space. Right now you're falling toward the center of the Earth. You don't notice it because the ground pushes back, holding you up. But if that ground were to vanish, you wouldn't suddenly start falling. You'd simply keep doing what you were already doing, without interruption. That is the essence of freefall. Step off a ledge and you don't create a new motion. You just stop resisting the one that was already there. The same thing happens on the grandest scales imaginable. Every astronaut aboard a spacecraft orbiting Earth is falling. Not upward, not downward, just endlessly sideways, missing the planet over and over again. We call this an orbit, but physically it's a fall, a perfect continuous fall that never ends. The craft isn't weightless because gravity is gone. It's weightless because everything inside is falling at the same rate. The walls, the instruments, the astronauts all moving together. That's why when they float, they're not defying gravity. They're obeying it perfectly. Imagine throwing a ball forward. The harder you throw, the farther it travels before hitting the ground. Throw it fast enough, about 28,000 kilometers per hour, and the ground curves away beneath it as quickly as it falls. It never lands. It just keeps falling around the Earth forever. That's what a satellite is, a rock in permanent free fall. This idea is so counterintuitive that it took humanity centuries to understand it. To us, falling has always meant moving down, but in the language of the universe, down doesn't exist. There's only direction, the path curved by gravity. Orbit isn't the opposite of falling. It is falling seen from a wider lens. The same is true for the moon. It's not hanging motionless in the sky. It's plunging toward Earth at every moment. But as it does, Earth curves away beneath it, so the fall becomes a loop, a graceful arc that has lasted for billions of years. That's why we never see it crash. It's always falling, always missing, always returning. And so are we, every one of us, every city, every ocean. The entire surface of the planet is caught in this endless fall, locked in a dance around the sun that began long before life ever appeared. It's easy to believe the sun is holding us up, but the truth is simpler and stranger. We are falling toward it, and the only reason we don't collide is because we're falling fast enough to keep missing. The universe doesn't need a hand to keep us in place. Gravity doesn't push or pull like some invisible string. It simply sets the stage and motion does the rest. When you float, when you orbit, when you move, you're following the most natural path the universe allows. Every orbit is a fall that never ends. Every world is a stone flung so fast it keeps missing the heart it's falling toward. And every second of your life, whether you feel it or not, you're part of that same silent motion. The apple falls for a few seconds. The moon has been falling for 4.5 billion years, and our planet will keep falling for billions more. For most of human history, falling was something we understood only with our eyes. We saw objects drop to the ground, we felt the pull in our muscles, but we didn't know why. Why does everything seem drawn toward the Earth? And why do the heavens, the sun, the moon, the stars seem to follow different rules entirely? For centuries, people believed they were separate worlds. What happened in the sky belonged to the divine. What happened on the ground was ordinary. Then one quiet idea would erase that boundary forever. Isaac Newton looked at the simplest thing, an apple falling, and saw something universal. The same rule guiding the apple also governed the motion of worlds. Gravity wasn't local, it was everywhere. He realized that the familiar downward pull we feel is not a special isolated effect of Earth, but a universal interaction linking every object to every other object in the cosmos. The apple's fall and the motion of the moon are 2 pages of the same story. One law, one universe. Newton expressed this idea with a breathtakingly simple equation. Every object in the universe attracts every other object, with a force proportional to their masses and inversely proportional to the square of the distance between them. 2 stones, 2 stars, 2 galaxies. It doesn't matter. The rule is the same. This idea changed everything. For the first time in history, the laws that govern the ground and the heavens were unified. The apple falling beside Newton's chair obeyed the same law as the planets circling the sun and the stars drifting through space. There was no longer a special realm above the clouds. The entire cosmos was connected by the same invisible thread. And this thread wasn't just a poetic idea. It could be measured, calculated, predicted. With it, Newton could compute how far a cannonball would travel if fired fast enough. He could predict the paths of comets, the timing of eclipses, the orbits of planets. He turned falling into mathematics, and mathematics in turn revealed the hidden architecture of the universe. Perhaps the most revolutionary part of Newton's idea was that gravity works both ways. The Earth pulls the apple down, yes, but the apple pulls the Earth upward too, just imperceptibly, because the Earth is so massive, every object pulls on every other. You are pulling on the distant stars right now, and they are pulling on you. Gravity became more than just a familiar sensation beneath our feet. It became a universal language, spoken quietly between every grain of matter in existence. It decides the shape of planetary systems, the structure of galaxies, the formation of stars. Falling isn't an exception, it's the default. This idea did more than explain how things move. It gave humanity a way to navigate the cosmos. Centuries after Newton's death, his equations still guide spacecraft to distant worlds. We use his laws to sling probes around planets, to land on moons, to aim telescopes at exoplanets orbiting faraway stars. Every maneuver is a silent conversation with gravity. But even Newton's brilliance had its limits. His equations told us what gravity did. They did not tell us what gravity was. Why should 2 objects separated by empty space reach toward each other at all? What was this invisible influence that crossed the void? That question would wait nearly 200 years for a man who would offer an even stranger answer. An answer that would turn the very fabric of space and time inside out. Newton's idea of gravity ruled for centuries. It sent ships across oceans, planets across the sky, and spacecraft to the moon. But it carried a quiet, unsolved riddle. What exactly was this invisible force reaching across empty space? How could the Earth pull on the moon without anything in between? In the early 20th century, one man offered an answer so radical it changed our picture of reality itself. Albert Einstein did not see gravity as a mysterious pull. To him, it was geometry. Imagine space not as a blank, rigid stage, but as a soft fabric that bends when something heavy sits on it. A star, a planet, even your body, everything with mass pushes down on this fabric. Other objects moving nearby don't feel a force pulling them. They simply follow the curves in that fabric. They fall not because they're being dragged, but because space itself tells them to. This was Einstein's great leap. Gravity isn't a force, it's the shape of space-time. It's hard to overstate how profound this is. The Earth isn't pulling the moon toward it. The Earth is bending the space-time around it. The moon is just coasting through that curve following the straightest path available. A geodesic, as physicists call it. This is why astronauts in orbit feel weightless. They're not escaping gravity. They're moving along space-time's natural curves. Gravity hasn't disappeared. They've simply stopped fighting it. Even you standing on the ground are trying to follow that curve, but the floor pushes back, holding you in place, preventing you from falling along your natural trajectory. What we call weight is not gravity pushing down, it's the ground pushing up. Resisting the full spacetime is urging us to take, and here's the most astonishing part. Mass doesn't just bend space, it bends time too. Near a massive object, clocks tick more slowly. Every fall is not just a movement through space, it's a slide through time. This is why Einstein's theory doesn't just describe falling, it reveals its true nature. When an object falls toward a planet, a star, or a black hole, it's not being yanked downward. It's simply doing what it would always do in curved spacetime. Follow the easiest path. This is why two satellites in orbit don't need engines to keep moving. They glide effortlessly along those curves. This is why planets stay in orbit for billions of years without slowing down. And this is why even light, the fastest thing in the universe, can be bent by gravity. It isn't that gravity reaches up and grabs it. The light is just following a straight line through a curved universe. The beauty of this idea is its simplicity. Einstein replaced an invisible force with something deeper, a kind of cosmic landscape. Objects don't tell each other how to move, they tell spacetime how to bend, and spacetime tells them how to move. This is why falling is universal. A feather, a hammer, a star, a beam of light. They all fall along the same curves, because they all live in the same geometry. When Einstein first proposed this, it sounded impossible to prove. But in 1919, during a total solar eclipse, light from distant stars was observed bending around the sun. The stars hadn't moved, spacetime had. And humanity saw for the first time gravity not as a pull, but as a shape. It's a strange realization. Falling is not something happening to you. It's the universe itself gently guiding your path through its curved stage. You're not being dragged, you're following the map written into the fabric of reality. And once you understand that, the question changes, not why do things fall, but what is the shape of the fall? Because in Einstein's universe, the shape of spacetime decides everything. It determines how stars move, how galaxies form, and ultimately, how time flows. Every fall is a journey through space, but more quietly and far more profoundly. It's also a journey through time. Near Earth's surface, you don't notice it. Seconds feel the same, clock seems steady. The fall of a stone looks like nothing more than acceleration. But the universe measures time differently from us. Where gravity is stronger, time itself slows down. If you place two clocks, one on a mountain peak and one at sea level, they won't agree after a while. The lower clock, deeper in Earth's gravitational well, will tick a little slower, not because the gears turn differently, but because time itself is flowing at a different rate. This is not an illusion, it's measurable. Gravitational time dilation is one of the most precisely confirmed predictions of general relativity. GPS satellites have to correct for it every second. Without those tiny corrections, just microseconds each day, your navigation would drift kilometers off course in a matter of hours. What's remarkable is why it happens. Einstein's curved spacetime isn't just a stage for falling, it's a clock. The closer you get to a massive object, the deeper you fall into its well, and the slower time runs relative to the universe around you. Falling isn't just a change in position, it's a shift in the tempo of existence. Now imagine falling towards something more massive than Earth, a neutron star, a black hole. The difference becomes extraordinary. For an outside observer, someone falling toward a black hole seems to slow down, their movements stretching their clock, crawling to a halt at the event horizon. From their own perspective, nothing strange happens. They fall freely, crossing the boundary in moments. But to the rest of the universe, their time has almost stopped. Falling in this extreme sense is not just movement through curved space. It's movement through a warped river of time. The closer you are to a massive object, the steeper that river becomes. And at the edge of a black hole, it becomes a waterfall. Time doesn't just slow, it plunges. Even Earth participates in this cosmic effect. When astronauts orbit above us, they're not just floating. Their clocks are ticking ever so slightly faster than ours. The difference is tiny, but it accumulates. After 6 months in orbit, an astronaut is a fraction of a second younger than they would be on the ground. Falling shapes time gently for us, violently for stars. This means every fall, whether it's an apple dropping or a star spiraling toward a black hole, is also a time shift. Every object in the universe experiences time at its own rhythm, set by the depth of the gravitational well it's falling through. Even light is affected. A photon climbing out of a gravitational well loses energy, its wavelength stretching, its color shifting to red, a cosmic signature of time running differently at its origin. This is what makes gravity so unlike any other interaction. It doesn't just decide where things move, it decides how they experience time. Where there is no mass, time flows straight and uniform. Where there is mass, it curves, slows, twists. Falling is how matter moves through that landscape, a movement written into time itself. So the next time you watch something fall, remember that beneath the motion you see, there's another motion you don't. A drift through the hidden contours of time. If you throw a stone, it arcs through the air and falls to the ground. Throw it harder and it travels farther, but if you could throw it fast enough, something strange would happen. It would keep missing the ground. Not because gravity stopped, but because the curve of the Earth dropped away beneath it as quickly as it fell. That stone would never land. It would circle the planet forever. Now imagine scaling this up by a few orders of magnitude. Replace the stone with Earth. Replace the ground with the sun. This is what it means to orbit a star. It's not floating. It's falling perfectly sideways. The Earth is plunging toward the sun at every moment. If it were standing still, it would crash into the solar furnace in just a few months. But it isn't standing still. It's moving forward at about 30 kilometers per second. That forward motion bends into a loop, an endless path where our planet keeps falling, and the sun keeps missing. This delicate balance between gravitational pull and lateral motion is what makes orbits possible. Too slow and Earth would spiral inward, vanishing into the sun. Too fast and it would escape altogether, flung into the darkness of interstellar space. We exist in the razor-thin middle ground where falling and motion are perfectly matched. What makes this remarkable is that nothing is holding Earth up. There are no invisible strings, no force counteracting gravity. Orbit isn't a battle between two opposing powers, it's a harmony between motion and geometry. Earth isn't resisting the sun, it's obeying it. And this dance isn't unique to our planet. Every object in the solar system is caught in the same falling loop. Mercury close to the sun races at nearly 48 kilometers per second. Falling along a tight curve, the distant Neptune drifts slowly. Its orbit wide and long, comets plunge in from the frozen edge of the system, whipping around the sun in wild, graceful arcs. Each one is simply falling with a different rhythm. These orbits aren't static. They precess wobble and shift over time. Gravity is patient but relentless, tugging every world along its curved path. The result is a cosmic clockwork that has endured for billions of years. For us, this perfect orbit is more than just a path through space. It's the reason we have seasons, the reason temperatures remain stable, the reason life has time to emerge and evolve. If Earth's orbit tilted too wildly or drifted too far, our world would freeze or burn. We survive not because gravity is gentle, but because motion and gravity have found a fragile, exquisite balance. This is the quiet truth behind our orbit. We are not standing in space looking at the sun. We are falling around it, endlessly, silently, caught in a precise gravitational embrace that decides everything about our world, from the length of a year to the fate of every living thing that's ever existed. Every orbit has a beginning, every star, every planet, every moon. Before they could fall around something, they first had to fall into something. Long before Earth was a blue marble circling the sun, there was only a cold, dark cloud of gas and dust. Silent, vast, For millions of years it drifted through space, weightless in appearance. But inside that cloud, gravity was always at work. Every atom, every grain of dust was pulling on every other, whispering the same universal language Newton described. Over time, those whispers became a chorus, and the cloud began to collapse. The process was slow at first. Tiny fluctuations in density, perhaps born from ancient shock waves or quantum ripples, gave gravity a foothold. Wherever the cloud was slightly denser, gravity grew stronger, pulling in more material, making it denser still. A runaway fall had begun. As the cloud collapsed inward, it didn't just shrink. It spun faster and flattened into a disk. This is a fundamental property of falling matter. When it loses height, it gains speed. When it collapses, it organizes. At the center of this swirling disk, pressure built up. Temperature climbed. Atoms slammed together with such violence that fusion ignited, and a star was born. Our sun is the product of that ancient fall. It wasn't placed at the center. It emerged there, forged by the weight of gravity, crushing a cloud into light. Around it, leftover gas and dust kept falling, colliding, sticking together. Tiny grains became pebbles. Pebbles became boulders. Boulders became worlds. This is how planets are made, not from chaos, but from collapse. Gravity doesn't just pull things down, it sculpts them. It turns drifting dust into structured systems. Each planet is the frozen memory of that first colossal fall, but the collapse never really stops. Even now, the sun is still pulling on everything around it. The planets are still locked in their endless arcs. Comets still dive inward from the frozen edge of the solar system, like ancient messengers carrying the memory of the cloud we came from. What's remarkable is how gravity does all this without effort. There is no blueprint, no hidden hand arranging the planets, just matter, and the simple rule that everything attracts everything else. Given enough time, falling builds stars, falling builds planets, falling builds entire solar systems. The orbit of Earth today is just the aftermath of that great collapse. Every sunrise, every passing season, every heartbeat of this planet is part of a story that began when a cloud of hydrogen decided to fall. There's a quiet truth about every star. Its life is a battle against falling. A star is born when gravity crushes a cloud of gas until fusion ignites, and from that moment on it lives by pushing back. The furious heat from fusion swells outward, countering the relentless inward pull of gravity. For millions or billions of years, this cosmic tug-of-war holds the star in balance. But no fire burns forever. When the fuel runs out, the star's light falters, its outward pressure fades, and gravity doesn't, without anything left to resist it. The star begins to collapse inward. At first, this fall can be gentle, a red giant shedding its outer layers, leaving behind a dense ember. But if the star is massive enough, the collapse doesn't stop, it accelerates. The core is squeezed to unimaginable densities. Atoms are stripped apart. Protons and electrons fuse into neutrons. If even that isn't enough, the collapse punches through every known form of matter, crushing it past the point of no return. Space itself caves in. A singularity is born. A black hole is not an object in the usual sense. It's a region of space-time where the fall becomes absolute. There is no ground, no stable orbit. Inside this invisible boundary, the event horizon, every path leads inward. Even light, the fastest thing in the universe, cannot escape the fall. From the outside, a black hole looks deceptively calm, empty space, nothing to see. But near its edge, the laws of physics begin to twist. Time stretches, distances warp. A falling object slows from our point of view, its image frozen and red-shifted into darkness. But to the object itself, nothing special happens. It crosses the horizon without fanfare, and continues falling forever. This is gravity at its most extreme, a place where the inward pull is no longer something you can fight, or even balance with motion. There is no sideways path to escape, no velocity fast enough to miss the center. Once you cross that line, the fall isn't optional, it's geometry. These cosmic abysses are scattered throughout the universe. Some are the corpses of dead stars, others are supermassive millions or billions of times heavier than the Sun, lurking at the hearts of galaxies. Even our own Milky Way is anchored by a silent gravitational engine that shapes the galaxy around it. And here lies the ultimate truth of falling. When gravity wins completely, when no force can hold anything up, falling doesn't end with a crash. It becomes a destination, a one-way journey into a place where space-time itself collapses. Black holes are not monsters in the dark. They are the purest expression of gravity's power, the final chapter of what happens when falling has nowhere left to go. For a long time we thought galaxies floated like islands in a calm sea of space. Majestic, isolated, still. But the universe has never been still. Every star falls. Every planet falls. And entire galaxies fall too. Our own Milky Way is not resting in some cosmic void. It's plunging through the fabric of space-time. At hundreds of kilometers per second, our galaxy, together with its neighbors, is being pulled towards something vast, something hidden, a gravitational center so immense it bends the flow of hundreds of billions of stars. Astronomers call it the Great Attractor. We can't see it directly. It's shrouded behind dense walls of dust and light, masked by the plane of our own galaxy. But we can feel its pull. Every galaxy in our cosmic neighborhood is drifting toward it, drawn by an invisible hand. This is not orbit. This is not collapse in the usual sense. This is falling on a scale so large that it stretches across hundreds of millions of light years. Imagine an ocean current, so slow you cannot feel it, but so powerful it carries entire continents. The Great Attractor is that current, a gravitational river flowing through the cosmic web. We, along with thousands of galaxies, are caught in this silent drift. We're moving through space at more than 600 kilometers per second. We don't feel it because everything around us, the sun, the planets, the stars, is moving too. Like a leaf carried downstream, we're part of the flow. And the Great Attractor isn't alone. Far beyond it lies Laniakea supercluster, a titanic basin of gravity so large it defines an entire region of the observable universe. It's not a structure we orbit, it's a gravitational landscape, and we're sliding down its slopes. This is the hidden architecture of cosmic motion. Galaxies don't just expand away from each other because of cosmic expansion, they also fall together, gathering into clusters into superclusters, forming an intricate web of flows converging on massive attractors. Every filament, every node, every cluster is shaped by billions of years of falling. Even on these colossal scales, gravity is patient. The journey of our galaxy toward the Great Attractor will take billions of years. We may never reach it. The accelerating expansion of the universe may stretch the fabric of space faster than we can fall. But the pull is there. A faint but relentless tug that guides the great migration of galaxies. It's strange to think about. The stars overhead, the familiar constellations, the solar system itself. None of it is fixed. We're all passengers on a galaxy that's falling towards something vast and unseen. Not a cliff, not a pit, but a gravitational basin woven into the structure of the cosmos itself. Falling doesn't end with planets or stars or black holes. It stretches across the entire universe, guiding rivers of galaxies through the darkness. Every orbit, every collapse, every drift, all of it is part of a single cosmic current, and we are riding it. When astronomers measured how fast stars orbit around their galaxies, they expected something simple. Closer stars should move quickly. Distant stars far from the center should move slower, just like planets in our solar system. That's what Newton's laws predict. That's what logic demands. But when they looked, they found something impossible. Stars at the edges of galaxies were moving too fast, far too fast. At those speeds, they should have flown off into the void long ago. spiraling away like stones flung from a sling, and yet they stayed. The galaxies held together, something unseen was pulling them in. This was the first great clue to one of the universe's deepest mysteries. Dark matter, an invisible substance that does not shine, does not reflect, does not absorb light at all, but it has mass, and mass means gravity, and gravity means falling. Every galaxy is wrapped in a vast halo of this unseen matter. It extends far beyond the visible disk, creating a gravitational well much deeper than what we can see. The stars aren't orbiting an empty space. They are falling through a hidden landscape. It's almost like watching leaves swirl in a wind we can't feel. We see the motion fast, smooth, impossible, and from that motion we infer the invisible force shaping it. Dark matter is not some exotic detail on the edge of physics. It is the dominant sculptor of galactic motion. Without it, galaxies would not hold together. Without it, they would tear themselves apart. And this isn't limited to a few galaxies. The entire cosmic web, clusters, superclusters, streams of galaxies, is threaded together by dark matter. It forms a vast skeleton beneath the visible universe. What we see, the stars, the gas, the brilliant spiral arms, is just a thin film of light draped over a colossal invisible structure. When galaxies fall toward one another, they're not just pulled by what we can see, they're sliding down the gravitational basins carved out by dark matter. When clusters merge, dark matter shapes the collision. When stars orbit, it holds their paths steady. Even the motion of our own Milky Way through space is guided by this hidden gravity. We are falling always, not just toward visible stars and galaxies, but toward something we can't see at all. It's a strange realization. The cosmos we observe, the brilliant tapestry of stars, is not the main story. It's the shadow of something larger, heavier, quieter. A gravitational structure that defines where everything falls. We don't yet know what dark matter is made of. It might be unknown particles, or something more exotic entirely. But we know it's real because we can see its fingerprints. In the way the universe moves, gravity is its voice. Falling is its signature. When we look deep into the night sky, we see scattered points of light, galaxies shining like islands in a dark ocean. But if we could step back far enough, if we could see the entire universe as one structure, it wouldn't look random at all. It would look like a web, a vast, intricate network of filaments and nodes, billions of light years across. This is the cosmic web, the hidden skeleton of the universe. It is the shape that gravity has drawn. Over 38 billion years of falling. In the beginning, matter was almost perfectly smooth. Tiny quantum fluctuations amplified during the early expansion gave gravity just enough unevenness to work with. Where there was slightly more matter, gravity grew a little stronger. More material flowed in. The well deepened. The fall accelerated. Over time, those tiny ripples became rivers. Galaxies didn't appear everywhere. They formed along these gravitational rivers, streams of matter sliding down into filaments. Where filaments intersected, the fall intensified. Clusters formed, superclusters emerged, and eventually the great attractors of the universe took shape. It's a strange kind of architecture. Gravity doesn't build by pushing things into place. It builds by letting them fall, slowly, inevitably. The universe sculpted itself by following the flow of its own gravity. Dark matter is the hidden frame behind this sculpture. It makes up most of the mass. Its gravity guides ordinary matter gas dust stars into the filaments we see today. Every galaxy, every star, every cluster is a drop of light caught in an invisible gravitational river. The vast voids between filaments aren't truly empty. They're simply places where matter has fallen away, where gravity has drawn it elsewhere. The result is a pattern both chaotic and precise, a cosmic network so large that even light takes hundreds of millions of years to cross a single strand. What's remarkable is how similar this structure looks at every scale. Stars fall into galaxies, galaxies fall into clusters, clusters fall into superclusters, and superclusters flow along these colossal filaments, like beads caught in cosmic streams. This is the shape of the universe not as a static map, but as a frozen moment in an endless fall. Every filament is a trace of motion. Every cluster is a place where matter has gathered at the bottom of a gravitational basin. And those basins are still deepening. Even today, the cosmic web isn't finished. Galaxies continue to drift along these filaments, colliding, merging, reshaping the universe as they fall. Billions of years from now, many of these rivers will merge into fewer, larger structures as the great gravitational engines continue their silent work. The shape of the cosmos is not a blueprint. It's a memory, a record of where matter has been falling. Since the beginning of time, before galaxies, before stars, before planets, the universe was smooth, not empty, not silent, but astonishingly uniform. In the first few 100,000 years after the Big Bang, matter and radiation were intertwined in a hot glowing soup. Everywhere you looked, the temperature was almost the same, the density almost perfectly even, but not quite. Hidden in that uniform sea were tiny imperfections, fluctuations as small as 1 part in 100,000. These were the first cracks in the stillness. They weren't galaxies or stars or even atoms bound together. They were ripples, minuscule variations in density seeded by quantum processes and amplified by cosmic inflation, and that's all gravity needed. Where the density was slightly higher, gravity became slightly stronger. Where it was stronger, it pulled in more matter. Where more matter gathered, the pull deepened. It was the beginning of the great cosmic cascade, a chain reaction of falling. Over millions of years, those tiny ripples grew. The universe expanded, but gravity worked patiently, turning gentle hills into valleys, valleys into wells, wells into rivers that would one day become filaments and clusters. The cosmic microwave background radiation we observe today is a fossil of that moment, a map of those first gravitational whispers. When the universe cooled enough for atoms to form, light broke free and streamed across space. But matter pulled by gravity began its slow inward drift. There was no grand explosion forming galaxies, no sudden collapse, just falling everywhere all at once over billions of years. Those tiny overdensities became the cradles of future structures. Some would grow into galaxies, others into clusters, and others into the vast cosmic nodes anchoring entire regions of space. Everything from the orbit of Earth to the path of galaxies across billions of light years was already encoded in those faint ripples. In a way, the universe has never really stopped falling. It's been doing it since the first second. Gravity didn't emerge later to shape what existed. It was there from the beginning, quietly guiding the flow of matter. The moment matter itself came to be. This is one of the most profound truths in cosmology. All the complex motion we see today, the swirling galaxies, the dancing stars, the great migrations of clusters, is just the amplified echo of those first fragile imbalances. Everything began as a whisper. Gravity turned it into a chorus. If you could freeze the universe in that ancient moment and press play again, it would all unfold the same way. The rivers of matter would still slide down the same invisible slopes. The same filaments would form, the same galaxies would rise, the same falls would happen. We are living inside the long tail of that first gentle tumble. Time has a direction. A glass shatters but never reassembles. Smoke disperses but never flows back into the match. Stars burn their fuel but never spontaneously grow younger. This irreversible flow is what we call the arrow of time, and at the heart of it lies something unexpected. Gravity. In the earliest moments after the Big Bang, the universe was smooth, extremely smooth, and that smoothness meant something profound. Low entropy, low disorder, a state balanced on a knife's edge. But gravity doesn't like smoothness. A smooth universe is unstable. The tiniest irregularities grow into wells, wells into structures, structures into galaxies and stars. Gravity amplifies imperfection. And as it does, entropy increases. Here's the strange part. Most forces in nature push things toward uniformity. Heat spreads energy, disperses, but gravity works the other way. It creates structure, it clumps matter together, forms stars, planets, clusters, black holes, and in doing so, it drives the universe toward a higher entropy state. When a cloud of gas collapses under gravity, the gas becomes hotter, denser, more chaotic. The outward simplicity of a sphere hides a wild increase in microscopic disorder. This is why stars shine. This is why black holes are born. Every fall, whether it's an apple or a galaxy, is a small step along the arrow of time. This connection runs deep. Without gravity, the universe would simply expand and cool, becoming thinner, colder, emptier, but not more structured. Time would still pass, but it would be quiet, uneventful. Without the irreversible drama of collapsing stars and merging galaxies. With gravity, time acquires texture. Each gravitational fall marks a break in symmetry, an event that cannot be undone without violating the statistical flow of entropy. Once a star forms once matter clumps, the universe has moved forward, and it won't go back. Even black holes, the ultimate endpoints of gravitational collapse, carry enormous entropy. In fact, the entropy of a single black hole can exceed that of all the stars in a galaxy combined. This means the greatest increase in disorder isn't when things fall apart, but when they fall together. The arrow of time isn't just written in broken glasses or burning stars, it's etched into the way the universe falls. Every collapse, every merger, every orbit slowly decaying is a one-way trip forward, and this is why we remember the past but not the future. The universe began in a low entropy state, and gravity has been guiding it toward higher entropy ever since. Falling is not just motion through space, it is the unfolding of time itself. If the universe had never fallen, time might still exist as a coordinate, but it wouldn't feel like time. No stars, no light, no evolution, no history. It is the act of falling structure forming entropy rising that gives time its direction. The universe falls forward, and so does time. Every heartbeat, every breath, every sunrise is possible because the Earth is falling. It's not just a poetic idea. Gravity is the silent architect of everything life depends on. It shapes the star we orbit. It fixes our distance from it, and it holds the thin film of air that keeps us alive. Our planet is trapped in a perfect gravitational dance round the sun. This isn't a coincidence, it's a requirement. Too close and the oceans would boil. Too far and they would freeze solid. We live inside a narrow habitable zone, a fragile balance set by the interplay between sunlight and falling motion. This is why the Earth's orbit matters. Because falling along the right curve means receiving the right energy. Gravity also holds our atmosphere in place. Without it, the air would simply drift away into space. Every molecule of oxygen, every drop of water vapor, every layer of protection that shields us from radiation. All of it is here because our planet is heavy enough to keep it. Every breath is borrowed from a well of gravity, but the role of falling goes deeper than that. Inside the Earth, gravity squeezes rock and metal, driving convection in the molten core. This motion creates a magnetic field that wraps the planet like a shield, deflecting deadly solar wind and cosmic particles. Without it, the atmosphere would be stripped away, and the surface would be sterile. Gravity also sets the pace of our days and seasons. The tilt of Earth's axis, the shape of its orbit, the pull of the moon, all orchestrated by falling. These cycles regulate temperature, climate tides, and currents. They create stability, the one thing life needs most to endure. Even the sun itself, the source of all our energy, exists because gravity once collapsed a cloud into a burning star. The warmth you feel on your skin began as a fall billions of years ago. Every living organism is powered by energy released from a cosmic collapse long past, and gravity doesn't just make worlds habitable, it holds them together long enough for life to arise. Stars burn for billions of years because gravity and fusion are locked in balance. Planets orbit steadily, giving evolution time to unfold. Tides driven by the moon's pull may have nurtured the first fragile ecosystems at the edges of ancient seas. Life isn't an interruption in the universe's falling motion. It's a byproduct of it, an emergent pattern shaped by forces that have been at work since the beginning. We are not separate from the fall, we are its consequence. When you stand on the ground and look up at the sky, you're not just seeing stars, you're seeing the infrastructure that makes your existence possible. A planet held together by gravity, bathed in the steady light of a star born from collapse, protected by fields forged deep in its core. Without gravity, there would be no stable orbits, no atmosphere, no oceans, no sun, no life. Falling is not the enemy of life, it's the reason it exists. Gravity doesn't stop at the surface. It reaches deep all the way to the heart of the world. When Earth first formed, it was not the calm blue world we know today. It was a storm of fire and stone. Asteroids collided, dust gathered. Each impact added more mass, and with more mass came more gravity. This relentless pull crushed the growing planet under its own weight, heating it from within. That ancient heat never fully went away. Gravity keeps it alive. Deep beneath our feet, the pressure is unimaginable. Iron and nickel are squeezed into a dense core. Temperatures soar higher than the surface of the sun. This is not just leftover warmth, it's gravity at work, converting the energy of countless falls into a furnace beneath our world. Inside that furnace, something extraordinary happens. The molten outer core flows and churns, stirred by heat escaping outward. This movement of charged metal generates Earth's magnetic field, a vast invisible shield that protects the planet from the solar wind. Without this field, our atmosphere would have been stripped away long ago, and life might never have found a foothold. Above the core, in the thick layer of rock called the mantle, gravity drives another kind of motion. Hot material rises, cooler material sinks. This slow, endless overturning mantle convection is the heartbeat of the planet. It pushes and drags on the crust above, shaping continents, lifting mountains, opening oceans. The continents you stand on are not fixed. They drift, collide, and tear apart over tens of millions of years. Each movement is powered by heat, and the heat is held, concentrated, and sustained by gravity's squeeze. Volcanoes erupt because mantle plumes rise. Earthquakes shake because plates grind together. These may seem like violent accidents, but they're part of a deep organized flow that gravity set in motion billions of years ago. This hidden engine does more than reshape the planet. It feeds life. Volcanic activity recycles carbon, regulating the atmosphere and climate. Tectonic movement creates habitats, drives nutrient cycles, and stabilizes temperature over geological time. The world beneath us is not inert. It is alive in a gravitational sense. Even the ocean you see on the surface owes its existence to this interior engine. Gravity holds the pressure that keeps Earth's interior active. Without that internal weight, the core would cool too quickly. The magnetic field would fade, the plates would stop moving, and the climate would drift toward extremes hostile to life. We often look up to the stars when we talk about gravity, but sometimes its most important work is happening far below our feet. Every mountain, every tectonic ridge, every drop of molten iron spinning deep inside the core is part of the same cosmic story. Falling built the planet, and falling keeps it alive from the inside out. Worlds don't last forever. Even the most vibrant planets eventually grow quiet. Their fires fade. Their cores freeze. Their gravity remains, but its heartbeat stops. Inside every rocky planet heat is a memory of ancient collisions, of relentless compression, of gravitational energy trapped deep within, but that memory can run out. As billions of years pass, a planet's interior slowly cools. The churning metal in the core becomes sluggish. Convection weakens. The dynamo that powers its magnetic field sputters and dies. The invisible shield collapses. Without that shield, the solar wind begins its slow, patient work. It strips away the atmosphere molecule by molecule, bleeding the sky into space. Radiation pours in unfiltered, water evaporates and is lost. Temperatures swing between brutal extremes. The surface once alive becomes bare and silent. We can see this story written across the solar system. Mars, once a world of rivers and lakes, is now a frozen desert beneath an unprotected sky. Its core cooled, its field faded, the solar wind tore away its air, and what was once warm and wet turned cold and dead. Even Mercury tells the same tale, its interior long frozen, its surface scorched by the sun, its magnetic whisper barely audible. It is a planet whose inner fall has already ended. When a planet's interior still moves, it can shield itself, breathe, evolve. But when gravity inside grows quiet, a world begins to age in silence. This is the slow death of a planet, not an explosion, not a dramatic end, but a cooling, a slow fading of the engine that once made everything possible. Mountains stop growing, volcanoes go extinct, the sky thins, the ground freezes, and the world forgets it ever burned. Even Earth will face this one day. Our core will cool, our shield will falter, and the sun, swollen into a red giant, will finish what time began. The falling inside will finally stop, but the gravity outside will remain. A cold planet is not a planet without gravity. It's a planet where gravity has run its course, where the energy born from its ancient fall has finally dissipated. A world that no longer shapes itself from within. Gravity built the world. Gravity kept it alive. And in the end, gravity watches as it grows silent again. Everything that falls has an end. A planet cools, a star burns out, a galaxy drifts. And one day even the universe will grow old. Right now gravity is still winning. It builds stars from gas. It sculpts galaxies. It draws clusters toward one another in silent rivers of motion. But gravity can only work with what it has. It needs contrast places of high density and low density, a landscape down which things can fall. As time stretches forward, that landscape begins to flatten. Stars burn their fuel and fade into embers. Black holes devour what they can and then wait in silence. Galaxies drift farther apart, carried on the swelling tide of expansion. The universe grows colder, thinner, quieter. Trillions of years from now, new stars will no longer form. The last red dwarfs will gutter out. The great engines of gravity will fall silent, not because gravity has vanished, but because there is nothing left to fall. Even black holes, the ultimate monuments to collapse, will not last forever. Through Hawking radiation, they will slowly leak their mass into the void. One by one, they too will fade, leaving behind only a sea of cold particles drifting endlessly apart. This is the heat death of the universe, a time when entropy reaches its maximum, when no energy remains to be rearranged, when no gradients exist for things to fall down. It isn't an explosion, it isn't fire, it's the opposite. A stillness so vast it erases the memory of motion. In that far future, gravity will still be written into the fabric of space, but it will have nothing left to shape. No clouds to collapse, no stars to ignite, no orbits to hold. Every well will have flattened, every structure will have dissolved. The universe will not end with a bang, it will end with a long, slow exhale, a fade into perfect equilibrium. A state where falling has no meaning. Because everywhere is the same, this is not a tragedy. It's a consequence of how the universe works. Every orbit, every collapse, every heartbeat of gravity moves energy from order to disorder, from difference to uniformity. This is the arrow that began with a whisper at the dawn of time and ends with silence. The cosmos began in a hot, dense, uneven state. It ends cold, thin and smooth, and somewhere between those two infinities, everything we know, every star, every planet, every thought, is just a moment in the universe's long fall towards stillness. When that day comes, there will be no more falling, not because gravity has died, but because the universe has reached its final perfect rest. For most of cosmic history, gravity ruled. It gathered dust into stars, stars into galaxies, galaxies into clusters, clusters into rivers flowing toward massive attractors. It seemed like the universe would forever be defined by falling. But then something changed. Billions of years after the Big Bang, astronomers watching distant supernovae found something strange. Galaxies weren't just drifting apart, they were accelerating away from each other. Space itself wasn't just expanding, it was speeding up. This was not gravity's doing, it was something else. Something that behaves like a pressure woven into the fabric of space-time itself. They gave it a name that captures how little we understand it. Dark energy. Dark energy is not a force like gravity. It doesn't pull objects together. It stretches the stage beneath them. Imagine standing on a rubber sheet that's quietly expanding beneath your feet. No matter how hard you run towards someone far away, the ground between you grows faster than you can close the distance. On small scales, gravity still wins. Planets stay in orbit. Galaxies hold themselves together. Clusters remain bound for now. But beyond those islands of stability, space is accelerating outward, carrying everything away from everything else. And the faster it stretches, the harder it becomes for gravity to connect distant parts of the cosmos. One by one, galaxies will slip beyond our cosmic horizon, not because they're moving through space, but because space itself is expanding between us. Eventually, only the closest cluster, our local group, will remain visible. The rest of the universe will fade into darkness. This is gravity's quiet defeat, not a violent battle, a slow erosion of its reach. Falling depends on differences in density, on gradients, on the ability to pull distant things together. Dark energy flattens those differences. It stretches everything apart faster than gravity can respond. In a future dominated entirely by dark energy, the great rivers of galaxies will dry up. There will be no new attractors, no new structures. Everything will drift into the night. Even if gravity never truly disappears, its arena shrinks, its voice grows softer. The universe will not stop falling, but it will fall into silence, trapped inside shrinking islands of matter, surrounded by an endless accelerating void. And that's the final irony. Falling gave shape to everything, but in the end, the universe itself will fall into the one thing nothing can escape, the expansion of its own fabric. We began this journey with something simple, a stone falling, a planet orbiting, a galaxy drifting, a universe unfolding. What looked like stillness was never still. From the smallest atom to the largest supercluster, everything is in motion, everything is pulled, everything is falling. You are falling right now, around the sun, through the galaxy, along the great gravitational river flowing toward distant attractors. The ground beneath you doesn't hold you still. It only pushes back against the curve of space-time that gravity has drawn. The stars above are falling too. They orbit invisible centers. They slide along the skeleton of dark matter, woven through the vast web that gravity has spent billions of years building. Even that web was born from a whisper. Tiny ripples in the early universe that began the Great Cascade. Every structure that exists is a monument to falling. Planets formed because dust fell inward. Stars ignited because gravity squeezed. Galaxies gathered because the universe was uneven. Black holes emerged where the fall never stopped. Falling shaped our world from the inside too. It forged our molten core, our magnetic shield, our breathing sky. It gave us a place where life could begin, and the stability it needed to endure. But even falling has its limits. Entropy grows, energy spreads, and as dark energy stretches the universe ever faster, the reach of gravity shrinks. One by one, the great structures will drift out of sight, not because gravity failed, but because the stage beneath it changed. The universe began with a fall, and one day it will end in stillness. Yet in between those two infinities, falling gave us everything. Every star, every orbit, every heartbeat. We are the brief bright pattern written in the middle of that descent. Everything falls, and we are part of that fall, not standing above it, not apart from it, inside it. Our lives, our history, our world are a ripple in a cosmic motion that began long before us, and will continue long after we're gone. Everything falls, and in that fall, the universe became what it is. From the core outward, the galaxy unfurls, not in straight lines, but in grand curling arms that sweep through space like frozen waves. They are the most recognizable feature of our galaxy, and also one of its most misunderstood. The spiral arms are not solid structures. They are patterns, density waves moving through the galactic disk. Imagine traffic on a highway. Cars flow, but the traffic jam itself holds its shape and drifts slowly forward. That is how these arms work. Stars' gas and dust flow through them, but the arms themselves are the jam, the places where matter bunches up for a while. There are several primary arms in the Milky Way. 2 of them dominate the outer disk, and 2 smaller arms weave closer to the center. Our own star, the Sun, is not sitting on a major arm. Instead, it lives in a small spur between them, a bright lane called the Orion Arm. This is like standing on a side street between 2 galactic highways. The spiral arms rotate more slowly than the stars themselves. Each star races ahead and then eventually drifts back into the arm again, a rhythm that repeats over hundreds of millions of years. This difference between stellar speed and pattern speed is what keeps the arms from winding up and disappearing. They are stable, flexible, and persistent. Inside these arms, new stars are born. As gas clouds enter a denser region, they are compressed. Gravity takes over and they collapse into brilliant young clusters. This is why spiral arms glow so brightly. They're full of hot, short-lived stars blazing with blue light. When these stars die, the next generation is already forming nearby. The arms are both cradle and graveyard. But these elegant shapes are not smooth. They are threaded with dust lanes, dark rivers of gas and interstellar grains that cut across the light. These dusty regions block visible light but glow in infrared, revealing cold nurseries hidden behind their veils. The same dust that hides the heart of the galaxy also weaves through its arms like smoke in water, and the arms themselves are not perfectly flat. The outer disk of the Milky Way warps upward and downward like a slow, gentle wave. This warp is a scar, evidence of gravitational encounters with smaller galaxies that once brushed past and twisted the edges. From above, the Milky Way would look like a glowing pinwheel, with a bright bar in the center and spiral arms stretching out in soft arcs. From within, it's harder to grasp. We can only map it through the positions of stars, the movement of gas, and the faint signatures of hydrogen. These arms are the living rhythm of the galaxy. They shape the flow of gas, the birth of stars, and the journey of our own solar system through space. We're not stationary passengers. We are riding the spiral. The Milky Way is not built from stone or steel. It is built from stars, each one a sphere of plasma, forged by gravity and burning for millions or billions of years. Together they shape the galaxy's light, its weight, and its history. Astronomers estimate there are 139 sao in our galaxy. Perhaps in hier hon most are small faint red dwarfs, barely visible even with powerful telescopes. A smaller fraction are stars like our Sun, bright enough to dominate their surroundings. And a tiny rare few are massive giants, shining with the brilliance of thousands of suns, living fast and dying young. These stars are not evenly scattered. They form patterns, layers, and families. Most belong to the galactic disk, where they orbit in vast, nearly circular paths. Here, younger stars are common, formed recently in the spiral arms. They burn hot and bright, often surrounded by gas and dust. Farther out and far above the plane of the disk lie the ancient populations. The stellar halo is home to some of the oldest stars in the galaxy, stars that formed more than moi batinam truki, long before the Sun was born. They are poor in heavy elements, their light softer, colder. their orbits tilted in every direction like scattered seeds. Between these extremes are the star clusters, stellar families bound by gravity. Open clusters are loose gatherings of young stars, like fireflies caught in the same breeze. They drift apart over time. Globular clusters are different. They are dense, ancient, and resilient, spheres of hundreds of thousands of stars orbiting the galactic halo. They are fossils, living witnesses of the galaxy's earliest days. Some stars move at ordinary speeds, others do not. A few rare outcasts are hypervelocity stars, flung out of the galactic center or torn free by gravitational encounters. They cross the galaxy at incredible speeds, on paths that may never return. And while each star is a single point of light to the naked eye, many are not alone. Binary and multiple star systems are common, with two or more suns orbiting a shared center of mass. Some whirl tightly together, others drift far apart, locked by gravity in an elegant silent dance. Every star contributes to the Milky Way's gravitational fabric. They move, collide, evolve and die. Supernovae enrich the gas between them with new elements, feeding the next generation of stars. In this way, the galaxy is not static, it is self-renewing, and somewhere out on a minor spiral spur, round an ordinary yellow star, on a tiny rocky world, a species looks up and wonders how many suns there truly are. The Milky Way does not end where the stars fade. Beyond the glowing disk, past the spiral arms and clusters, lies a vast invisible structure. It has no light, no colour, no edges we can see, but it outweighs everything that shines. This is the dark matter halo. Dark matter is not made of stars, gas or dust. It does not emit, reflect or block light, but it has gravity, and gravity is enough. It holds the galaxy together, binding stars that should have flown away long ago. Without it, the Milky Way's spinning disk would unravel like a carousel with no axle. Astronomers first uncovered this invisible mass by studying the speed of stars. Near the galactic center, stars move quickly. Farther out, they should slow down. Just as planets orbit more slowly the farther they are from their star, but the stars at the edge of the galaxy do not slow down. They race through space too fast for the visible mass to explain. Something unseen is anchoring them in place. That something is a halo of dark matter. Its mass is estimated to be around 10 times greater than all the stars' gas and dust combined. Its size stretches well beyond the visible disk, perhaps more than 300,000 light-years from the galactic center. The halo envelopes the Milky Way like a transparent cocoon. We cannot photograph it, but we can trace its pull. The rotation curve of the galaxy, a plot of stellar speeds versus distance, remains almost flat, instead of dropping away. That flat line is dark matter's signature, an invisible hand gripping the stars. Globular clusters orbit through this darkness, swinging in long, elegant arcs around the galactic center. Streams of ancient stars curve and bend, their paths shaped not by what we see, but by what we don't. Dark matter is the skeleton of the galaxy. It sets the scale of the Milky Way, defines the strength of its gravity, and stabilizes its spinning disk. It even shapes the orbits of the satellite galaxies, tiny companions like the Large Magellanic Cloud, guiding them along unseen rails. We still don't know what dark matter truly is. It might be made of exotic particles, or something even stranger, but its effects are undeniable. Every star, every orbit, every motion we see happens inside this invisible halo. The stars are the face of the Milky Way. Dark matter is its bones. The Milky Way was not born in peace. It was built in battle, shaped by collisions, mergers, and a slow gathering of cosmic debris. Its smooth spiral structure hides a violent past, more than 13 billion years ago. The first building blocks of our galaxy were small, chaotic dwarf galaxies. They were bright, unstable, and crowded with young stars. Gravity pulled them together over cosmic time. They collided, merged, and became something larger, a growing gravitational seed that would evolve into the Milky Way. The outer halo of the galaxy still carries the fingerprints of these ancient encounters. Across the sky, tidal streams stretch like ghostly ribbons, rivers of stars torn from galaxies that no longer exist. They are not random lines of light, they are fossils, recording the collisions that built the galaxy's skeleton. One of the most important events in this story is known as the Gaia Sausage Enceladus merger. Billions of years ago, a dwarf galaxy plunged into the Milky Way. Its stars and clusters were absorbed, leaving behind tilted, stretched orbits that still sweep through the halo today. This single merger reshaped the early disk, thickened it, and changed the structure of the galaxy forever. The Milky Way continues to grow in the same way. Right now it is absorbing the Sagittarius dwarf galaxy, a small fragile neighbour being slowly torn apart. Its stars stream across the sky like light from a shattered necklace, wrapping around the Milky Way as they fall inward. Each merger leaves behind more than stars. It leaves behind energy, angular momentum and structure. The central bar may owe some of its strength to ancient impacts. The warp in the outer disk may be a ripple frozen in place from long-vanished galaxies. We can still read this history by measuring how stars move. Modern surveys like the Gaia mission track the positions and velocities of billions of stars. From this data, astronomers can rewind the clock, reconstructing the hidden choreography that shaped our home. The Milky Way is not a quiet island. It is a survivor of countless collisions, each one leaving behind traces in its halo, its disk, its very shape. And the story is not over. Another collision far greater than any before is already on the horizon.